when no sand drain is used, how much will be the degree of consolidation? And then the sand drain diameter is given, and it is given. I mentioned that it can be square pattern, it can be triangular pattern. So this is, for this case, it is given square pattern. And you need to calculate the average degree of consolidation of the clay with sand drain for the time when the degree of consolidation without drain is 20. So degree of consolidation EU is equal to given 25%. So there are two situations. One, the soil is isotropic. So meaning the permeability in the horizontal and vertical direction is the same. And when the radial directions, the permeability is twice than the vertical one. Okay. So now, what are the things that are given? So just writing, this is problem number 4. Sorry, man, this. It's fine. And then suddenly what happened? I don't know what is going on. What can you see now? It's nothing. So can you see now? Okay, I don't know what is going on. So depth of the strata is given, it's so erratic. I don't know why it is like this. So H is given is 6 meters over here. Not very clear, I don't know why. And then the diameter of the sand drain, that is it readable? It's so bad, right? 30 centimeter, that is 0.3 meter. I don't know why. I need to calibrate or what, I don't know. And then the effective radius is given. Effective radius, I think something wrong. Is given, that is RW is 0.15 meter in this case. Spacing of the well. Spacing of the well is given 3 meter. Okay. So because it's a square pattern, so we need to find out how much is the radius of influence zone. So basically we have a sand drain here. This is sand drain, and this is another sand drain. This is another sand drain. So we need to find out like how much is the influence zone. So basically for this one, this will be the effective diameter. So this is the effective diameter. This is the effective diameter. This is the effective diameter. So we need to find out how much is the distance from here to the center of this to this, the influence zone. So if I say for the square zone, if I say this is R, so that value will be for a square pattern 0.564 times the spacing of this well. So in this case, the spacing of the well is 3. So and then you can calculate how much is the value of R. So that will be 1.692 meter. So now the thing is we need to check what is the value of n. So I have given the problem. There is a table I've given with degree of consolidation, and n value is equal to r by rw. This is the r I just now calculated, and the rw is the radius of the well, and then the time factor is given. For different u value for the radial directions, and then also the time factor. So with a different n value. Okay, from there, first thing we need to calculate what is the value of n in our case. So n is basically r by rw. Okay. So r is just now we calculated 1.192 divided by rw is the radius of the well. The sand rain is 0.3 in meter. So that will be approximate. So this will be this is rw is 0.15, correct? We just calculated. So this will be around 11.28. So approximately we can say n is 11. Okay. So now for our case, the degree of consolidation u r in radial direction, it says is 25%. Okay. So you can calculate how much is that. So basically, this is the vertical direction. So we generally don't write, correct? So vertical direction for 25%, we calculate how much is the value of TV or time factor. That is pi by 4 e by 100 whole square. So easily you can calculate that, and that value will be coming around 0.0491. Okay, 0.0491. So TV. So TV now will be, again, you need to use that same equation. TV is equal to CV times T divided by height of drainage, that H whole square. Can you read it really? This is, I don't know why, it's very erratic, the pen. So here, from here, you can easily find out how much is the value of T. So T is equal to, so TV, you can calculate, TV just now we calculated from this degree of consolidation, E is equal to 25%. That is 0.0491 is equal to CV. CV, you can, you need to calculate for the time being. So CV is given, but this is in the vertical direction. And T divided by height of drainage over here, you need to calculate that what is the value of HDR. So that is basically 2 times R whole square. Okay, so that's the one you need to calculate. So basically from here, you'll be getting around TR. You will get TR is equal to, from here. So basically, as I mentioned, this is for the vertical situations, correct? So this is for the vertical. So vertical situation, the T is equal to 0.0491 H squared divided by CV. This is, I'm just writing Z. This is the vertical direction. So we need to find out for the time factor TV for the radial direction. So that is the value we can calculate. So TV in the radial direction is equal to CV in the radial directions times T divided by that 2R whole square. That's the one I just mentioned just now over here. So from here, what you can do, that TVR you can calculate, right? So TV radial directions is equal to here TVR divided by 4R square. Okay. And the T you can calculate just now from the vertical direction. So you can use that value, you just substitute over here. So that is 0.0491 times height is, in this case, is 6 meters, 6 square divided by that. I'm just not writing this CV. This is CV in vertical directions. So basically, we don't write that CV in vertical directions, correct? So this is, one is radial, one is vertical. So what you can do, so TVR, you can calculate from here. So sorry, TVR you can calculate is equal to so TVR is equal to CVR. So ultimately, if you calculate this one, so you will be getting around TVR is equal to you'll be getting around so TVR is equal to 0.154 times CVR divided by CVZ. So this is basically this is for the radial, this is for the vertical direction. Okay. So now the thing is, we need to for isotropic soil, so that the K radial and the K vertical, or we can say KZ, Z in the vertical directions, so it's the same. So in that situation, so CVR by so basically CVR by CVZ vertical directions is equal to 1 in this case. So now what you need to do for the isotropic case, so what are the things you need to check? So N is equal to 11, you have given. So from now, TVR is equal to, you can calculate that TR is equal to, if this is CV by TR is equal to 1. So basically TV, I can write over here that, sorry, TR is equal to 0.154. Okay. So if from here, from here. So TR is equal to 0.154. And then from for N is equal to 11 and TR is equal to 154. So you can calculate that the degree of consolidation U is equal to approximate 44% from the table. Okay? So 44% is 0.44. And then you need to use the equation like, that EU1 minus EU is equal to that, the equation 1 minus EUZ, that is the vertical directions, times 1 minus EU radial direction. So you can calculate from here what is the degree of consolidation for combining this radial and horizontal. Okay. So radial and the vertical. So from here, you can easily calculate that the EU is equal to 0.58, 58. So 0.58, this is 58%. So you see that when there was no drainage, the degree of consolidation is 25%. Now, because of the sand rain, the degree of consolidation is increased to 58%. So I don't know whether, can you just really read it, whatever I'm writing? Because I cannot understand what I'm writing. Hello. Can you really understand what I'm writing? Because this pen is not very working properly.
Yes, sir. Yes, sir. There is option also. We can zoom here.
Oh, okay. But I cannot read what I'm writing. So anyway, so the second part of this problem is the radial permeability. So page. So basically, in that situation, so CVR is equal to 2 times CV vertical directions. Okay. So basically, it is K is equal to given KR is equal to given 2 times of KZ, that is in the vertical direction. So we can find out from there CV is equal to, also because K is equal to CVMB gamma W. So we can calculate what is the value of K with the same value of CVE. So CVR, this is CVR divided by CVZ, that is the vertical direction is 2 basically. And then TR is equal to, we already calculated, that is 0.154 times that CV by CR is 2 now. So we can calculate like a 0.308. So can I don't know what happened. Why is so basically what happened? The TVR, the radial direction is equal to 0.308 now. And again, you need to go to see the table for n is equal to 11 and TVR is equal to 0.308. What is the degree of consolidation in the radial direction? So UR percentage you need to calculate. So that is around, it will come around 91%. So that is 0.91. So from there, again, you need to use that the combined equation 1 minus U is equal to that 1 minus U vertical times 1 minus U radial. And from there, 1 minus U vertical is 0.25, correct? And 1 minus U radial is now 0.91 now. So you can easily calculate that this will be around 0.06, 0.75, 0.675, and then from there, if you calculate this, so from there ultimately you will be getting around 0.9325. So basically is 93%, approximately 93%. Okay. So when the radial permeability is twice that the horizontal permeability, again now the consolidation, degree of consolidation increased to 93%. Okay. So I really don't understand. I mean, whether you guys really can read it, whatever I'm writing.
No, sir, it is perfect.
Oh, it's perfect. Okay.
Yes, sir.
But then the next problem is it says the 5-meter thick of soil, soft clay above the impermeable bedrock requires preloading for the improvement. And so again, the clay has coefficient of consolidation is given, how long it takes 90% consolidation based on Terzaghis one-dimensional theory. So that is the first part is basically without anything. Okay. So now the second part is how long will it take that if you use 300 millimeter diameter of and 5 meter long free draining sand drain with spacing is given and square pattern, and then obviously it is going to rate of consolidation is going to increase. So how much will the average degree of consolidation in year according to Barron's solutions? So first thing is problem number 5. First thing is you need to calculate that degree of consolidation U is equal to what? The 90%, right? So U is equal to 90%. So and then you can calculate the two way. One is PV or time factor. You can calculate by using that from the table, or you can use that equations. If it is less than 60%, pi by 4 U by 100 whole square. If it is more than if it is 90%, so it's more than 60%. So the equation is 1.781 minus 0.933 log of 100 minus U. So easily you can calculate that for 90%. So this will be 0.848, right? So that is the time factor. So now how much the time is going to take? So T is equal to, again, use the same equation, TV time height of drainage, height of DR whole square divided by CV. So you need to just remember same equation that TV is equal to CV times T by height of drainage whole square. So that's the one. So from here, you can easily find out what is the value of T. So T is equal to TV times height of drainage square times CV. And from here, everything is given. So TV, just now we calculated 0.848. What is the height of drainage in this case? So it is given just 5 meter thick. And so it is one-way drainage. You see the clay above is impermeable bedrock. So it is one-way drainage. So here H could be just 5. If it is a two-way drainage, then it will be 5 divided by 2. And then CV is given also. So CV is 1.5 times 10 to the power minus 7. And then that, and again, you need to convert that in days. So obviously you need to multiply, this is meters square per second. So 24 times 60 times 60, you calculate. So then you will get in days. So that will be 1636 days. Okay. So this is without anything. Okay. Without anything. So now we need to use that the sand rain, right? So now again you need to calculate how much is the equivalent diameter of the unit cell. So if I say this is equivalent diameter of the unit cell, cell is equal to 1.13 times of S. So again, there are several equations. So for the square pattern and for triangular pattern, this is the equation. So here 1.13, and how much is the S over here? This is 1.5, right? So spacing is 1.5 meter. S is the spacing. Sometimes, some books they use S spacing is equal to S. Sometimes some books spacing is equal to L. You need to be careful which one. So basically 1.5. So this will give you 1.695 meter. This is the equivalent diameter of the unit cell. So diameter, this is talking about the diameter. So you need to find out then the diameter ratio. So diameter ratio you can calculate. So sometimes we call it ND, and that is DE divided by DC. Okay. And so here DE is just now we calculated 1.195 divided by diameter of the sand grain is 300 millimeters. So this is 0.3 meter, and then this will give you like a 5.65. Okay, the N is 5.65. So now you need to calculate that the degree of consolidation for this case. So there is an equation for F and D. So we need to use that. And then basically you need to use that degree of consolidation, UR is equal to 1 minus e to the power 8 divided by F and D times TR. So what is F and D? So there is an equation for that. F and D is given by this equation, ND squared divided by ND squared minus 1 ln ND minus 3 times ND squared minus 1 divided by 4 times ND squared. So this is the equation. So you can find out what is the value of F and D. So everything is known, so this is 5.65. So ND is equal to 5.65. So if you calculate ND is equal to 5.65 everywhere, so we'll be getting around 1.045. So that is the value of F and D. F and D is 1.045. So only thing is here you need to assume that the coefficient of consolidation in the horizontal and vertical direction is the same. And in that case, so TR, you will be getting CVR in the radial directions time T divided by this DE whole square. So that is equivalent diameter. So for the cell, we already calculated that. So if we can use that, CV is given 1.5 times 10 to the power minus 7, and again 24 times 60 times 60. You can calculate, and the T is basically you need to calculate for 1 year. So again, you need to multiply with 365 days. divided by DE, you already calculated, that is 1.695 whole square. So TV, you can calculate from here. So degree of consolidation, so again, this is in radial directions. So you can calculate this one is 1.646. And if you know that, then you can use this equation again. Just plug it in over here, TV, this should be in there. This is radial direction. So if you plug it in over here in this equation, so you will get U radial will be, so U radial will be 1 minus e to the power 8 divided by FDN is, FDN you already calculated, that is 1.045. Power is now multiplied with now 1.646. 646. So if you calculate that, you will be getting around 100%. So that's so basically what happened. So when you use sand drain, the degree of consolidation is increased by 100%. Okay. So and then so that is so that is the problem number 6. Problem number no, that's problem number 5 now. So the problem number 6 is basically if there is a smear zone, as I mentioned earlier, like when there is some portion of the sand grain is mixed with the clay, and if there is, obviously the permeability is drastically reduced. So what is going to happen if there is a smear zone, that is problem number 6. So there, what is happening, if there is a smear zone, and then there is an equation for that, considering for the smear zone, if ND is given by this equation, Ln is a long equation, ND divided by NS plus KR divided by KS, Ln NS minus 3 by 4 plus pi V 2 times HDR minus Z times KR divided by QC. So this is the long equation. So you need to use that. And only thing is here, HKR by QC should be 0 when there is a free drainage. So in this problem, it says the free drainage, we assume that is the free drainage. So that part will be 0. And then basically what I need to calculate, so U is equal to, again, just use this equation, 1 minus e to the power 8 divided by Fm ND, times TR. So if you use that, so you'll be getting the value around 99.99%. So it's not 100%, a little bit reduced. Okay, so that is problem number 6. So now problem number 7 is very simple. There's nothing much to do. Basically, the PVD is a flat material, So basically, we need to find out how much is the equivalent. So PVD is a thin, it has some width and there's some the width and there's some thickness. So if you know all these parameters, so easily you can calculate. So equivalent diameters. So it is a flat stuff. So we're just doing it. How much is the equivalent diameter for this? So this is the so how much will be the equivalent diameter? So you can calculate for that. So D equivalent is for there is an equation for that so one factor is 0.9 times. So there are 2 equations. One by the Rixner. So that equation is basically, how much is the equivalent diameter, is how much is the width, how much is the thickness, divided by 2. It's very simple. So B is, for this case, is width is 100, is given. Thickness is given 6.25 millimeter. And then divided by 2. So that is very simple. So 61 millimeter is the equivalent diameter. That is very simple. There is another equations. You can find out DE is equal to alpha, alpha D, that value is 0.9 times 2 times of how much is the width B plus the thickness divided by pi. Okay. So if you use that equation, so you'll be getting around 61 millimeters. So a little bit different. So different people come up with different equations. So DE equivalent is 61. Other earlier one, it was 53, right? So that is problem number 7 is very simple. It's nothing much to do. Then problem 8 is, again, you need to find out the discharge capacity from this PVD, okay? PVD discharge capacity, and there is an equation for that. Discharge capacity, 7.84 Fs times Ks, Kr times H times dr whole square. And then, so from here, you can easily find out that the factor of safety is, so 7.84 times the factor of safety is given 5 in this case, and the permeability is given, that is 9. It's very simple, 9.5 times 10 to the power minus 8. And then height of drainage, obviously, is the length of the PVD, that is 10, so 10 whole square. So just very simple, 3.73 times 10 to the power minus 4 meter cube per second. That is the discharge. So it's very simple. Just everything you just write in this equation, you will get that how much the discharge through the PVD. Okay? So easily you can calculate. Then problem number 9 is important. Is basically there are PVD 15 meter long, 70 equivalent diameter is given, installed spacing is given 1.3. The triangular pattern, and permeability is given, horizontal permeability is given, vertical permeability is given, and the smear zone is given 2.5 times the PVD equivalent, and permeability is 1/3 of the vertical permeability also given, and allowable discharge capacity of PVD is given. Calculate the equivalent vertical permeability of the PVD for the input. So basically, what I need to do, you need to find out the equivalent permeability. So you need to understand that what is happening. So basically, just for example, this is a PVD. Okay, this is PVD, another one PVD, another PVD like this, right? So now this is just for example, this is impervious. Impervious. And the load is coming from here. Obviously, there should be some sand rain on the top. So now, because of that, these are all clay, right? So the clay water will go in this PVD from here also, and then it will go vertical directions. So basically, we have that K in the radial directions over here. We have K in the vertical direction also. K in the vertical direction, KB. So we need to calculate how much is the equivalent permeability. So basically, you need to calculate something like a K, how much is the K equivalent. So same thing earlier, the normal permeability is horizontal and vertical permeability. The K equivalent normally is just normal soil. You know that the K horizontal times square root of K vertical, correct? So this is the equation generally you use. But here, the equation is different. So K equivalent, this is the equation is 1 plus 2.5 times HDR whole square divided by so K equivalent is 1 plus 2.5 times HDR divided by FM ND times D square times KV, and then on the top KR, and this will be times K vertical. So this is the equivalent permeability. Now the thing is, again, you need to calculate what is the value of ND. So here again, so how much is the equivalent diameter you need to calculate first? So D is equal to 1.06 times the spacing is 1.5. So that one you need to calculate because it says triangular pattern. So D equivalent you can calculate from here. So 1.3 times 1.06, that is 1.378 meter. So that is the equivalent diameter. So we need to find out the diameter ratio, that ND, correct? ND is diameter ratio. I'm just writing here, diameter ratio. So that one is equal to, you can find out how much is the equivalent diameter. So 1.378 divided by the diameter of that, the PVD equivalent diameter is 75 millimeter. So that is 0.75. So you'll be getting around 18.37. 18.37. ND you calculated. So now you need to use the, you need to calculate the value of FM, ND, because here, because the smearing is also takes place in this situation over here. Okay. So what you need to do again, so FMND is a big equation again. FMND is equal to ln ND by NS plus KR divided by KS ln NS minus 3 by 4 plus pi Z 2 times HDR minus Z times KR by QC. So this is the equation you need to use. And from here, everything is given. So you already calculated that. So ln is the log, so base E. And ND is over here is 18.37. This NS is equal to 2.5 plus 6.5 times. So this is vertical permeability, 6.5 times it is given, 10 to the power minus 9. And then 8.3 times 10 to the power minus 10. ln, this is 2.5 minus 3 by 4 plus pi. Z over here is 7.5. You see the length is given. Okay. So sorry, this is Z is 15. Sorry, Z is height is 15. So and then 7.5 is the half. So basically the 5 by 4. So 3 by 4 plus pi times 7.5 times bracket 2 times 15 minus 7.5. And then again, the permeability is given over here. You can multiply with that. So 6.5 times 10 to the power minus 9 divided by 2.5 times 10 to the power minus 4. And if you calculate that, that one will come around 8.41. So 8.41 if, so basically FMND is going to come 8.41. And then you can use that equation in the last slides you mentioned. So you can calculate that that the K vertical equivalent, if you just plug it in all these value, then you'll be getting around 2.32 times 10 to the power minus 7 meter per second. Okay. So this is equivalent permeability. Equivalent permeability of the PVD improved soil. So we can find out that. So because horizontal and vertical permeability is changed, so basically you need to use this equation. The mid depth of the soil layer. So how much is this? So basically FMND we calculate at the mid depth, right? So that's why we use that. The Z over here is 7.5. Okay? So total is 15 meter long. So this is 7.5 mid depth. What is happening? Okay. So now the last problem is, you know, just problem at 10 is the vacuum preloading with PVD used to improve 20 meter thick soft layer, soft clay. Basically, the equivalent vertical permeability is given of the PVD imposed soil is 3 times before improvement. Determine the optimum penetration depth of PVD for the vacuum preloading. So you need to calculate that the PVD vacuum preloading. So there is a standard equation for that. So what I need to do, just for example, we have a PVD is up to depth, maximum penetration depth. Okay, so it's not that you. So over here, just for example, this is PVD, and the value of this KV1. Okay, so now, so this portion is that the drainage. This is the drainage layer again. This is the drainage layer, and top also there is a drainage layer, correct? Drainage layer, both layer, and then we need to find out that how much is this optimum value from here to this. So here in this drainage in this clay layer, the probability is that is KV2. Okay, KV2. So this one is when the PVD used, that part is KV1. This is KV2. So if you know that the KV1, so KV1 is the equivalent vertical permeability. So this is vertical permeability. This is KV2 is the vertical permeability of the soil below the PVD improved. So this is the PVD up to here. So this is below the PVD improved soils. That is the permeability. And H is the thickness of the soft soil. The total thickness is H. So and then HDR is the one you can easily calculate that. So age, as I mentioned, HDR, you can, so total age, this optimum, okay, the optimum penetration depth, you can find out optimum penetration depth is given by this KV1 minus square root of KV1 times KV2 divided by KV1 minus KV2. Okay, times H. So as I mentioned, so I don't know why this was, as I mentioned, this is a drainage layer. PVD is up to here, not the whole depth. And then, so this is the permeability for this KV1, and this is the permeability for KV2. And that's the one you need to know. You need to find out how much is the optimum penetrations from here to here, H optimum. So this is the equation for that. Okay. And this is the drainage here. This is the drainage layer also here. So if everything is given now, KV1 is, again, it says 3 times of the vertical, KV2. KV1 is 3 times K vertical. So that's why it is mentioned in the problem. The vertical improved 3 times, and then KV1 again, 3 times of K verticals, KV2 basically times KV2 divided by 3 times KV2 minus KV2. And then the height is over here is 20 meters. So you just multiply with 20. So easily you can calculate all this. So basically you can, from here, you can find out you will be getting around 12.7 meters. So that is the optimum penetration. Yeah, you can calculate the optimum penetration depth is while using this PVD vacuum preloading. All right. So I think I just stop here now, and then I'll just continue.
Vipender sir, I guess his mic or speaker is not connected at the moment. So if you can message him, or otherwise you can inform Senthil sir or Chori sir to message him, because his video is visible, but that mic sign is not visible also in the participants list.
Hello, can you hear me
Yes, sir,
now?
your mic is now connected.
Oh,
Kindly,
okay.
yeah,
Yeah, because
yeah,
I
now you
want
are
to
audible.
get rid of that the one, X pain. And but anyway, I don't think it was really good option, and whatever I explained, I don't know whether people follow or just the writing. Even I cannot read my own writing. So, but anyway, do you think that I should continue or just break for 5 10 minutes and then we can continue? Okay, okay. So now is around 7:30 there, correct? No, not 7:30 yet. 7:25. So 7:30, can you start? 7:30? Okay, okay. All right. I'm so sorry for this inconvenience. Okay. All right. Thank you.
Recording.
Can I start now? So can you see the screen now?
Recording in progress.
Okay. All right. So you can see the salt separation in that mixture, right? Okay, good. So again, welcome back. So now I'm going to talk about the salt separation. As I mentioned earlier, there are four major solid treatment methods. One is the mechanical one is this the hydraulic modification, get rid of the water, and then the chemical modification, and last one is the inclusions or using geosynthetic. So today I'm just going to talk about the soil stabilization with admixtures. Soil improvement with admixtures, obviously we need to add some chemicals into the soil. So basically, you need to add any type of admixture. So most of the time, we use Portland cement, ordinary Portland cement, or lime, or fly ash, or bitumen, or any other material. So basically, if you talk about the chemical stabilization mixtures used when mechanical method of stabilization is inadequate. So when you try with mechanical, it is not working. So in that case, you can use it. Or replacing an undesirable soil, the desirable soil is not possible. So, and it's too expensive. So in that situation, you need to use this soil stabilization. So just for example, we have a huge depth of soft clay, and we cannot just one method we mentioned earlier that the field replaced with a good soil. So sometimes it's not possible to, because the depth is too high, so you cannot replace. And then you can just improve only some portion of the topsoil by using chemical admixtures. So that is a viable option. So again, sometimes people use, as I mentioned, so like all these different type of chemicals, Portland cement, lime, or fly ash, or sometimes in combination of these, 2-3 chemicals together. Okay. So with admixtures, improving so basically what is happening, so when you add these chemicals into the soil, there is a chemical reaction, obviously. There's a chemical reaction takes place, and you need to understand that what is happening into the soil and what is forming after these chemical reactions. So improving the engineering property of the soil is often simply referred to the soil stabilization. This is soil stabilization. Some admixture of agent is good stabilizing some agents, some is not. So just for example, if you're using cement, for example, it is good for all type of soil. But if you're using lime, so that is not good for gravel type of soil. So it's only good for clay, for clay type of soil. So that's why it says some is good, sometimes it's not good. Agent also, stabilizing also undergo different reactions and require different conditions to reaction takes place. Again, we'll talk more about that. Therefore, it is important to understand this. So chemical reaction, what is happening when you add soil, you need to know the chemical composition of the soil, you need to know what are the stabilizer chemical compositions. And then when you mixing it, what type of reaction takes place. And then from there, you can choose what type of soil is the stabilizer is the most suitable for a particular soil. And obviously, you need to do a lot of trial and error test. And then you can find out how much is optimal. So the most commonly used, as I mentioned, the most commonly used the Portland cement, lime, fly ash, silica fume, blast furnace slag, or sometimes called the granulated blast furnace slag, calcium chlorides. So any type of stabilizer you use, what are the different reaction takes place? So just for example, using cement, what is the cement? We add water into that. What is the different reactions? Pozzolanic reaction between the calcium hydroxide and pozzolanic minerals of the soil. Again, you need to understand what type of clay mineral present. What type of clay you are trying to stabilize. What type of clay you want to stabilize. Whether it is, again, clay is less than 0.002 millimeter particle size, and the silt is 0.075 to 0.00 or 75 to 2 microns. But the main thing is that clay also, there are different types of clay, right? So whether it is illite, kaolinite, bonboronite, bentonite, depending on the type of clay, what type of different mineral present in that clay. So you need to use different stabilizing agent, and then also in combinations, and sometimes use what are the different doses. So, and then also, as I mentioned, so the ion exchange reaction takes place also. So what is the chemical reaction takes place? That's very important. So in order to understand the chemical reaction between the soil and the stabilizing agent, we need to understand the composition of the agent and their reaction with water. So water is the one that the reaction takes place, right? So in general, most of the cases when the particles are fine, the surface area is more, then the reaction will be more. Okay? So reaction will be more. Temperatures plays an important role. So obviously, the higher temperature, the reaction is more. We'll talk more in geopolymer soil stabilizations. So low temperature impact the pozzolanic activity reaction negatively. So we need more high temperature for more chemical reaction. So the minimum, the purpose of mixing of these additives. So again, for any type of stabilizer, when you use to clay type of soil, so what is happening? Increase the strength and stiffness, increasing, reduce the compressibility and deformation, reduce liquefaction potentials, control shrinkage and swelling, reduce permeability, seepage and water pressure, reduce slope instability, reduce erosion potentials, and reduce the potential detrimental environmental effect and the stabilized west side. Again, all these things as a very general purpose of this any mixing or salt stabilizer mixing. So first thing is I'm going to talk about the cement, and then we'll talk about the lime and fly ash and GTBS. Okay. So first thing is cement. So we need to know for what type of cements are there. So there are normal cement, there are modified cement, high early strength cement. Sometimes we need it. There are low cement, and there are sulfate resistant cement. So sometimes you need to see that there are some soil has a lot of sulfur or clay. So if you use cement, then there is a mineral form, ectringite, and instead of stabilizing it, so that the volume is going to increase, and that is not good. So there is a limit how much the whether. So in that case, what you are going to do instead of cement, you need to use some other type of material. So that's why there are sulfate cement is also there, and suitable soil type. So cement can be used for sand and gravel, mostly granular type of soil. Also suitable for fine grained soil. So obviously cement is suitable for all type of soil. So obviously if it is a clay type of soil, you need to add more quantity. We need to add more quantity. Low to medium plasticity, plasticity index is less than 30. So can be used also. So now when you add cement to clay or soil, what are the different reactions takes place? You need to understand that. So ion exchange reaction takes place. There will be flocculation, there will be pozzolanic reactions, carbonation reactions, and then also cement hydration. So that is the most important, cement hydration. So now, so when you talk about cement, you need to understand what are the different, how the composition of the cement itself. And then also the reaction of the cement and water to form cementitious compound, that is calcium silicate or calcium silicate hydrate. Or which binds that together. So it is when you add cement with clay, so it's a calcium silicate hydrate, calcium aluminate hydrate. These are the two minerals formed, and because of that, or ectringite or monosulfate aluminate. So these are the different mineral form. Because of that it glued together. Okay. So major gain of the soil cement treatment of the soil is increase again as I mentioned the general one, increase the strength and stiffness, better volume stability, less moisture sensitivity, control of frost and heat, and increased durability. Cement. Also, these days, people are more concerned about using cement because the production of cement itself generates a lot of CO2 and greenhouse gas, and so people are going towards like a calcium sulfaluminate cement instead of Portland cement, some other cement type of material, cementitious material. So as I mentioned, the reaction in general, we need to check. The Portland cement reacts with water to provide high strength immediately. So again, there are different types of cements are there. So this is the immediate initial setting time cements, immediate, that's quick cement. That can reaction will be much faster. Then the lime. So these are just general reactions. This is for the cement immediately it reacts. So lime it reacts with water. And again, what type of lime you're using? You use calcium hydroxide and provides no strength gain itself, but reacts with pozzolaniform soil to provide strength gain slowly. So what is happening sometimes is pozzolanic material. So just for example, we have a fly ash. This is class A, just for example. So this is pozzolanic material. So you need to add a little bit of lime, then it is going to react. Okay? So pozzolanic agent like fly ash, silica fume needs calcium hydroxide. For reaction. If enough CO2 is not available, the addition of this agent will not do any good. So again, the blast furnace slags need to activate before it can react. So again, these are the different. So we need to check the chemical composition first. You need to check the chemical composition of the soil, and then you need to understand what are the reaction going to take, and then you can use that that type of stabilizer. Reaction product from any agent mainly consists of calcium and siliceous compound with smaller amount of aluminum, iron, and other elements. So this is Portland cement, as I mentioned. So the particle size is 1 to 100 micrometer. And I'm not going to talk about how the cement is produced. Basically, it's a limestone and clay and put it in a clinker with high temperature, and it rotates. And then obviously we add some gypsum to delay the initial setting time. There are for the concrete, people use different other retarder, but for the soil is already there, gypsum. So surface area is higher, so more surface area means it is more reactive. Typical composition of the cement is, you see the calcium is the one that binds together, calcium oxide, 60 to 75%, 60 to 70%. Then silica is 17 to 25%. Alumina is 0 to 6%. So silica, alumina, iron, manganese, magnesium, iron, sulfur, these are the few things. And then calcium, we generally denote C, and silica is denoted by S, and the alumina is A. So when you say that CSA, so calcium silicate aluminate, these are the different abbreviations generally used. So cement is cement hydration. So there are 4 main components. I'm just going to go here. The composition of cement is tricalcium silicate, dicalcium silicate, tricalcium aluminate, and tetracalcium aluminum ferrite. So these are the 4 main components of the cement. And then tricalcium silicate and dicalcium silicate constitutes 75%. So when you add water, so these dicalcium silicate and tricalcium silicate is going to react with the water over here, and then it is forming calcium hydroxide is 25% of the hydrated cement, and then calcium silicate hydrate 50%. So that is the heart of the concrete. So calcium silicate hydrate, we call it CSH. Okay. So and the reaction of this tricalcium aluminate to form tetracalcium aluminate hydrate. So as I mentioned, so these are the 2 main things: tricalcium, dicalcium when you add it to the water, and then tricalcium aluminate, it will be forming tricalcium aluminate, and then tetracalcium aluminum fluorides also. So over here you can see tricalcium silicate hardens quickly. This is responsible for initial setting or early setting cement. So you can play with these different compositions, and you can make different type of cement. So C2S, dicalcium silicate, hardens slowly, and it contributes gain after 7 days. Tricalcium aluminates give a large amount of heat during cement hardening. Tricalcium aluminate fluorides hydrates quickly, but contribution is very little towards strength gain. So basically, it added to reduce the temperature of the clinker itself. So as I mentioned, so basically there are different components of the cement, and then how it reacts with water. So now when you add with the soil, you need to see the chemical composition of the soil itself. So soil is mostly the silica and alumina, correct? So silica, alumina, iron, there are 3 things. And then also how when you add these chemicals, how the chemical reaction takes place. And then finally, it is going to form calcium silicate hydrate, calcium aluminate hydrate, or calcium silicate aluminate hydrate, or maybe a tringite, or maybe the calcium monosulfate aluminate. So all components start reacting concurrently at different rate. As I mentioned over here, tricalcium silicate and dicalcium silicate, these are the 2 things react first. And then within first few minutes, cement releases some ions and some silicates, primarily because tricalcium silicate starts reacting. A tringite formation, this is the one the mineral formation starts, and heat is generated. And after 10 to 20 hours, it is difficult to water to penetrate the reaction. So basically, it is forming a calcium silicate hydrate gel, and the reaction and the heat evaluation subsides, but formation of a continues. Okay. So again, a is not good for sulfate when the sulfur, the clay present a lot of sulfur. Then a is a structure. Basically, it's like a flower type of structures. It increases its volume. That is not good. So when no more sulfate is available, gypsum provides the sulfate, the ettringite converted into monosulfate aluminate with a denser than ettringite. This is much more stable. Okay. So mostly when you add cement, so 50% of the cement reacts in 3 days, 60% in 7 days, and 90%. So that's why most of the time for any, even in concrete also, we calculate the strength after 7 days, 14 days, 28 days, like that. So initial, so that's the reason. So 50% cement reacts within 3 days. Okay? So hydration of calcium, tricalcium silicate or dicalcium silicate, as soon as water is added, calcium ion is released rapidly and hydroxide ions is formed. pH is going to increase. So that's when the pH is 12 in few minutes. So more pH is better. So it's the alkali and silica, because the silica is the alumina and the soil contain the alumina and silica, correct? So when pH is increases, then it will dissolve the silica and the reaction takes place, is forming a gel, calcium silicate hydride gel. So when the calcium hydroxide ion concentration reaches a certain threshold, calcium hydroxide crystallizes out of solution, and then a extremely fine poured calcium silicate gel is formed. Okay, and the specific surface of this gel is around 350 meters square per gram compared to the cement itself. So as I mentioned, the more surface area, reaction is more. Okay? So as this layer grows, water must penetrate through the layer and to get to the unhydrated tricalcium silicate and must diffuse through the gel. So basically, and then calcium silicate gel is very strong and considered the heart of the concrete, as I mentioned. And C2S, dicalcium silicate, reacts the same way, but at the slower rate. So again, as I mentioned, that which one is reacting first, that the dicalcium silicate, tricalcium silicate, tricalcium aluminate, tetracalcium aluminate fluoride, and what type of clay minerals are there. Hydration of tricalcium aluminate, there is no sulfate in cement, no gypsum is going to react with the water to form the calcium aluminate hydrate. And tricalcium aluminate reacts with the water again to form ettringite. And then again, ettringite is stable only for excessive, as there is excessive sulfate. Since the concentration of sulfate falls 24 hours, so obviously ettringite is converted into monosulfate. This is much better. And then, so these are the different reaction takes place, with the different composition of the cement itself. So now, so when you add cement to soil, what is happening? Basically, this is common for all stabilizer. And then, so reduction of the plasticity characteristics as made of a plasticity index, that is liquid limit minus plastic limit. Reduction in the amount of silt and clay particles, it is forming like agglomerations since particle size is increasing. Reaction increase in the California bearing is a test that is going to increase. Increase in the CS strength, that is UCS strength is also going to increase, and decrease in the volume change properties, obviously. Then that is the cement. Now, if it is a lime use, what is going to happen? So lime is, again, there are different types of lime. So one is like a limestone, that is agricultural lime, so we don't want that. So there is a quick lime, there is a hydrated lime. So and then composition of lime is basically the calcium oxide is a lime. So calcium oxide is the main composition, 90 to 94%. Silica is 1.5%. Alumina is 0.8. Magnesium oxide 1.7. So obviously, the quick lime is sometimes divided into two categories: hard burnt lime and soft burnt lime. So based on the residual CO2 left after calcinations. So over here, quick lime is basically calcium oxide. It's in dry form. So when you calcium oxide added with water, that will be forming a calcium hydroxide. That is a hydrated lime. There's a hydrated lime or sometimes a slaked lime. And then the dolomite, that is calcium or magnesium oxides. And then we have agricultural lime, that is calcium carbonate. So we don't want that in agricultural lime for the soil stabilization. Sometimes the lime also used, because when we add lime to the clay, so it generates heats. And sometimes instead of actual stabilizations, it can be used as a modifier just to reduce that the water content from the clay. So the quick lime is more effective than the slacked lime in terms of handling and transport. Agriculture and lime is not suitable for stabilization. Dolomite lime is not usually used as effective as hydrated or quick lime. So now again, what are the reaction takes place? So basically, lime is made from limestone and then consists of calcium carbonate. So basically, when you calcium carbonate, we heat it, so it will be forming CaO plus CO2, correct? Calcium oxide plus CO2. CaO is basically formed during the reaction. It's called the quick lime. So basically, that's why it's heated. So that's why it's the burnt lime also called. Slacked lime, you have to add with water, and then it's forming calcium hydroxide, formed in the slacked lime or hydrated lime, or sometimes in construction lime. In US here, most of the time people use like quick lime. It depends. Sometimes people use hydrated lime. Both has advantage and disadvantages. So hydrated lime commonly used to stabilize soil in US, hydrated limes, whereas quick lime is commonly used in Europe. So again, it depends. But I know over here in Southern Illinois, people use this, the quick lime also. The less pure form of lime are also available and sometimes used for stabilizing agent. So sometimes people are using even lime clean dust or cement clean dust, from the cement industry or lime industry. It's not the actual lime, but it's a waste, and we can use that also for the stabilizing purpose. So hydration of lime, we just mentioned again, quick lime, this CaOH2 plus heat, CaOH2 plus water plus pozolanite will be forming is calcium silicate hydrate or calcium aluminate silicate hydrate. We call it CaSG is similar to one often from the cement, but CaSH this contains alumina. Okay, so now when we add lime plus CMOS, there are short-term reaction and long-term reactions. So the short-term reactions, the hydration takes place quickly, flocculation takes place or ion exchange. Long-term is the cementation and the carbonation. So what is hydration? So basically it reacts quickly to water and producing hydrated lime. So that is CaOH2, generating considerable amount of heat and causing volume increase. Particularly beneficial some moist clay, as I mentioned, it can use for the drying the clay if it's too much of water. So in the placement of lime column and layer, the heat generation and expansion of the lime further enhances the consolidation process. So basically, remove the water. So remove the water is basically consolidation process. So hydration, then the flocculation. Flocculation, so when mixed with clay, sodium and other cation absorbed to the clay. Again, you need to know that the clay is negatively charged particles and what are the different minerals present and what type of clay you are talking about, whether it is 1:1 clay or 2:1, depending on that clay, and then maybe ion exchange and isomorphous substitution takes place. This change in the cation exchange complex agent affected the way of structural component of the clay minerals are connected together. Lime causes clay to coagulate, aggregate and flocculate. Okay, and the clay plasticity is reduced because of reaction, and they're making it more easily workable and potentially increasing the strength and stiffness. But again, for clay lime is not suitable for gravel or sand. It is only suitable for clay or maybe a little bit of silt. Cementation, again, the cementation is the main contributor of the reaction of the stabilized soil. Higher the surface area, more reactive is the process. Okay, more reaction will take place. So lime, again, that's the no dimensions. Lime is not suitable to improving clean sand or gravel. Okay? Cementation is, however, limited by the amount of available silica. Again, the silica there are different type of silica, and then when we add, that's why the pH need to be increased, and then the alkali silica reaction takes place. And increase the strength up to a point where all silica of the clay is used up. Okay? Then the last one is the carbonation reactions. The carbonation reaction of lime with CO2 in open air and voids of the ground forms relatively weak cementation agent. So again, if the CO2 is formed, that is inert, so we don't want that. Okay, so CO2 form will not react further with the soil. Okay? So if the carbonation takes place, so CO plus CO2 is forming CaCO3, so we want that. So benefit is the same exactly like for the cement. Also improved workability, increase the strength of unconfined compressive strength UCS value or California bearing ratio test value. Improve the volume stability, the sinkage and swelling behavior, drying and wetting behavior respectively. So basically, it's very basic for all stabilizers. These are the two common things people are using: the stabilizing agent or admixture, cement and lime. These are the two common. People are using these days for the last 15, 20, 30 years that different agent, but you have to be careful while using that different stabilizer agent or waste material people are using. Instead of dumping to the landfill, people are using that. Is much more sustainable, but you have to do the leaching test and other things. Otherwise, it will be a problem in terms of environmental point of view. So amount of lime required varies based on the characteristics of the material that need to be treated and desired degree of stabilization, how much the strength you need. Most of the cases is there are different people have studied different things. So 2 to 3% of dry weight of the soil is sufficient. So most of the time people use like a 6 to 8%, 6 to 8 to 9% of lime. So if you use more than that, the strength increasing strength is go down. Okay, so depending on the free available silica, right? For stabilization purpose, typically 5 to 10% of the weight of the dry soil is used. But again, as I mentioned, it can be up to 6 to 9%. So how you can find out the optimum lime content? So you can find out how much is the percentage of clay divided by 35 plus 1.25. So this is the given as per the Bargado. So how much is the optimum lime content to stabilize the clay? And also we need to check that different trials. So you take some clay and then add different percentage of lime and measure the pH. Okay. When you see the pH is at least 12.4, that is the lime percentage generally you need to use. Okay, but this will give you a preliminary study, and then immediately then you have to do more tests and to find out so how much is the optimum lime content. So some of the advantages and disadvantages of dry hydrated one. So this is the one. The advantages of dry lime can be applied 2 or 3 times faster than the slurry. This is very quick. But again, dry lime is not is effective in say drying out the soil. It's a dry because it's going to react and it generates heats and then it dry out the moisture easily. Disadvantage is dry lime produces a dusting problem and thus make it use undesirable in urban areas. Fast drying actions, so dry lime requires excessive amount of water also. So if you are using in hot season, that is not good. Some advantages and disadvantages of dry quicklime. So it's more economical. It contains approximately 25% more available lime. Greater bulk density for small sizes silos. Faster reaction with soils. So these are a few things you need to check. Disadvantage is field hydration, less effective than the commercial hydrator. Quicklime requires more water than the hydrated for stabilizations, which may present a problem in the dry areas, and the gaseous susceptibility to skin and eye burns. Again, quicklime that's the disadvantage. The slurry limes, that is the hydrated lime. So again, the dust-free application is more desirable from environmental standpoint. Better distribution to be achieved in slurry. Sometimes if you use dry, the mixing process is not good, then it will be a problem. The lime slurry method, the lime spreading and sprinkling operations are combined, thereby reducing the job. Dry one, you have to spread the lime first and then mix it, then spread water, and then you do the compaction and mixing and compaction. So here, everything is together. Slurry is there, just add it and mix it. The added heat when slurry is made for quicklime speed drying action, which is especially desirable for cooler weather. Disadvantages, application rates are slower High capacity pumps are required to achieve applicable application rate. Extra equipment required, therefore costs are higher. And then it's not practical for use when the soil is obviously when the soil is wet, so we can't use the wet slurry method, right? So this is how it looks like, the spreader, how they spray the dry lime, and then it makes it like it pulverizes, and then you add water, after pulverizes and stabilizes, they compact it, and then add water and then compact it, basically, and then left it for curing. So this is close to my campus. I just took some picture here. So first they spread the lime using this instrument, using that machine. And then this is the main mixer over here. You see, initially it was here, the lime was there. So when the truck is going with the mixer, so inside is a mixing process. And then when it goes, it is already mixed, okay? So this is already done. You see already one time mixes, they do 2 times. And then this is the same pictures. And then how it looks like, you can see here, there are lime mixtures. This is quite uniform mix of the lime with the soil. Okay. And after the mixing is done and spreading water, they use that the sheep foot roller or compactor. And then when the sheep foot roller is done, the compaction is done, obviously you need to use the field density test. What are the density? And then also later on, you need to collect the soil sample for UCS testing later on. So here, this is the nuclear gauge test. And to determine that how much is the field density, you can use any method. You can use even core cutter or a sand replacement method or water replacement method, a rubber bearing method. So lime stabilizations, as I mentioned, so most of the time is a mix it. This is one is just shallow mixings. There are deep mixings. You can make a lime column also. So these are the different equipments. Generally completed lime columns. So what is a soft soil? There is a mixer, inject unslacked limes, and then mixing tools. And with the compressor, they just mix it, and then forming a solid lime column, and then just lift it up. So it is basically from the bottom and then go up. So lime columns are extensively used in Sweden, Norway, and Finland, following purpose to improve the total and difference in settlement with lighter structures, increase the settlement rate, and control the settlement relatively heavy structures, improve the stability of the embankment and slopes. So more than 1 million tons limes are used in US for a modification. For the modification, as I mentioned, just to dry out the soil and stabilize it. Okay? And the lime is an excellent choice for the soft short-term modification of the soil. And the lime can be modified almost all fine-grained soil, but most dramatic improvement occurs when it's clay with high plasticity. As I mentioned earlier, this is the plasticity is going to reduce, reduction of the moisture holding capacity, swelling reduction, improved stability, and the ability to construct a solid working platform. Sometimes, when the soil is very soft, there are 2 methods. One is like a dry mixing method, and then shallow mixing method and the deep mixing method. Sometimes when the soil is really soft, use of cement or lime, and then mix it together. And the shallow mixing, just a little bit strength is increased, cure for 7 days or 3 to 7 days. And then when it is strong enough to hold that equipment, at least different boring machine and other, then you go there and then making a column like for the deep mixing for different, making a strong column, either cement or lime. So deep mixing column. Okay. So benefit of soil stabilization include substantial increase in the rational modulus values by factor of 10 or more cases, improve the shear strength, and then continuous strength gain with time, and then also long-term durability over decades. So again, we need to check. So when the soil is stabilized, so we need to go and check, do the test, how much the strength is improved. In the lab, generally, we do the UCS test, we do the CBR test, also to see the effect of dynamic load, we do generally resilient modulus test. The lime stabilization should be considered when the plasticity is more than 10, plasticity index is more than 10, or percentage of passing number 200, that is 0.075 millimeter is 25%. Okay. So requirement of lime stabilizations, the right combination of the material, adequate lime to keep polyonic reaction going, adequate strength to resist freeze thaw, and adequate compaction and moisture. There are a few things you need to check. Evaluation of lime stabilizations, as I mentioned, the Ellis and Grimm's method. So what you need to do, first you add soil and different percentage of lime and see how much is the pH. So it's a quick test. So 12.5, that is the minimum amount of lime is required. So and then you need to add more maybe, and then see when it is stable, pH is almost stable, then that is the minimum requirement. Optimum moisture content, you can find out also. There's some standard Proctor test, and you can find out. And the ECS test, so minimum is for like 100 psi, okay, the pound per square inch. So for ECS strength for stabilized soil. So again, so we need to check that. So mostly it is 50 psi, 50 to 100, depending on the situations. And there is a standard code you need to use for the stabilized soil. So this is some of the example, like how we can use this line column. So there is a line column, and then people are constructing on the top of there is a lightweight structures. It can be for embankment also. You can construct on this line column, and then it can be the same thing. The line column, there is an embankment on the top. It can be used for ground anchor, and there is a sheet pile wall and the ground anchor also. It can be used using this line column. And then there is you can use that footing or foundation also. So there is a chart over here. This is a Dunlop chart, okay, that can be used to calculate how much percentage of lime, depending on how much the thickness of the pavement you need to know, and then also you need to know the CBR values. So Dunlop design, they developed a design chart for clay subgrade modified with either lime or cement, with CBR of 5 or less, okay? And then noted that if the lime is being used, stabilized clay subgrade can be assumed that some tensiles tend to develop the modified layer. So here, this is the chart he will develop. So over here, so the chart for the design chart of the pavement of 150 millimeter thick of lime modified subgrade. So there are T, X, Y, and Z, 3 different coordinates, and then also lime modified CBR. And the subgrade CBR, you can calculate. So what you need to do, and then also you need to know that how much is the design load for the pavement, and then how much should be the granular cover, how much should be the base and sub-base thickness. All these things you can easily find out from this graph. So first thing is what I need to do, select a sufficient lime stabilizer to give 18 days CBR, at least 25%. So, and then from quadrant A, you need to find out how much is the CBR of the modified method over here. So first thing you need to check that the quadrant A at how much is the cover you need, how much is the subgrade value you need, okay? And then from there, how much is the modified CBR value you need, and then from there you just go down and you can find out depending on the design load and calculate how much is the granular cover you need. So the process is given over here, and from here easily you can calculate basically how much is that. So how much is the granular cover you need for this lime stabilized soil? Okay. So I'm not going to go in detail, but you can easily find out all these different quadrant A, B, and C, and then you can find out how much is the. This is for the subgrade soil CBR. This is for the subgrade soil with the lime modified. This is the effective CBR for the design load, and you can find out how much is the cover required for the lime stabilized soil. So this is the same thing again. So now the second one is, third one is basically we talked about cement, we talked about lime. Now these are the different other stabilizers like a blast furnace slag. So this is the waste from a steel industry, and this is, if it is grounded to fineness, approximately the same as cement, so that can be used because this is a coarse material. Sometimes people use, that's why you call it ground granulated blast furnace slag, so GGBS. And then basically you are increasing the surface area is much more reactive. So also here, you see the chemical compositions. Is calcium is the, again, 36% calcium, silica is 36%. The calcium is the more binding agent, right? That's more. And so basically, you see the rapid cooling create a more vitreous with high reactive slag, and slow cooling in crystalline or almost inert. So basically, again, if it is more amorphous, it's much more reactive. So how you can find out this amorphous and crystalline? So again, you need to do the chemical composition test, either using X-ray fluorescence spectroscopy. So you need to take some sample with microcrystalline wax, and then pass the X-ray and see how much is the percentage or different percentage of different chemical composition from X-ray fluorescence spectroscopy. So basically, it will give some signals or values, the peak, and you need to check that, run the actual sample, the actual silica, alumina, iron, pure one, and then you see how much is that. From there, you can calculate X-ray. So now these days, you just automatically, the instrument will give you. So basically, the XRF, you need to do XR, and then what are the different mineral forms? So that one you can, so how do you know this line and amorphous? So from the X-ray diffraction analysis, you can find out. And X-ray diffraction analysis also will tell you what type of mineral forms after this chemical reaction. That is the test you need to do, and then also do scanning electron microscope to see the microstructures. There are two tests generally we do for X-ray diffraction, and then also scanning electron microscope. So blast furnace slag cannot react with water in itself. It needs some activation. So like a pozzolanic material, COH also from cement or lime can provide activation, but alkalis and sulfate can also be activated. Once the activated reaction takes place, largely spontaneous due to its own calcium reactions. It's a pozzolanic material. So you add water and lime, then the reaction starts. And main product, again, the same as other for lime or cement, calcium silicate hydrate gel, and and then the calcium oxide and silicon oxide ratio is important. Reaction is temperature dependent, and the higher the temperature, faster the rate, and the mixing lime or cement can help raising temperature and speeding the reactions. Fly ash is again another industrial product, coal-based thermal power plant. So it's most of the time these particles are very spherical, and people are using for different purpose, for using in a cement or small soil separations. Because if you use in cement, so the cement in concrete can be more flowable. But sometimes these particles are hollow, and that is called sinospheres particles. Sometimes there are some particles are inside the hollow particle, there is another particle, some of pleurosphere. So that is also a problem. If you use in concrete for the soil, you can use it. So here the properties are fineness, vitreous content, and the loss of ignition of unburned carbon. If there is unburned carbon is more, that is not good. So and then vitreous content normally between 60 to 90%. Higher the vitreous content, better is it. So again, we need to see that the chemical composition. Again, here the calcium oxide is the main component, right? For the glue is that holds together is 1 to 40%. So here there are two types of fly ash. You need to know class F and class C. Class F is pozzolanic. It has less CaO. But class C fly ash has more CaO, so that is more calcium. We need more calcium, right? Because the cement and lime is more calcium. So if you want to use fly ash, better to use class C fly ash. So that is much more reactive. The problem is sometimes, if you use in concrete, class C has more sulfur also. So then, if you use in concrete, the problem is, the sulfur will form reacting with the water, forming sulfuric acid, and then again it will react with the reinforcement, and that is not good. And it will corrode the reinforcement. So we don't want that. So again, there is a concrete thing. So people are using, but the reaction mechanism is the same. Whether you use in cement, in soil or cement in concrete. They're the same alkali silica reaction, calcium silicate hydrate, calcium aluminate hydrate, or active gyrate. So again, you need to understand the class F and class C. You need to do first X-ray fluorescence spectroscopy, find out what are the different chemical compositions. Most of the cases, the class F is the calcium oxide, silica, and alumina. Silica, alumina, and iron. If it is more than 75%, that is class F. If silica, alumina, iron is less than 75%, less than 70%, mostly or 50%, so then it is called class C. But the calcium is more in that class C. Calcium is less, nearly 5 to 7% in class A fly ash. So hydration reaction is the same thing again. Reaction is slow, but it will increase in later stage. So again, when the cement or lime reacts with water, it forms calcium hydroxide to turn either calcium silicate hydrate or calcium aluminate hydrate. Reaction is temperature dependent. And also is, again, you see the fly ash is very heterogeneous. So again, you need to characterize the first, what type of fly ash, what type of, again, it depends on what type of coal you use, degree of pulverizations, temperature of the furnace, and the collection method. So there are not only fly ash, there are bottom ash, there are sometimes the fly ash and bottom ash mixed together, add with water, and then pump it to the lagoon. Here's the lagoon ash. These properties are also getting changed. So again, calcium hydroxide plus silica, the calcium oxide and calcium silicate and hydrate. So calcium CSH. This is with alumina, it is formed the calcium aluminate hydrate. So we call it CaH. So polymer reaction at time is temperature dependent and may continue for a long period of time. Sometimes, if you need the strain quickly, you need to use cement or quick setting cement, or calcium sulfaluminate cement. But if you need, slow reactions, we don't need the strain quickly. So you can use fly ash or any other material or GGBS. But in long run, the strain will be almost close to that fly ash or GGBS or cement. So again, there are several relations are here. You can calculate how much is that. There's a major component, the silica, alumina, iron. If you calculate that calcium oxide percentage divided by the silica, alumina percentage, if it is more than 1.75, then it is better. Such that the order of reaction takes place, the hydration modulus must be 1.7. So basically, you can see here, calcium oxide should be more, right? So if it is the numerator should be more than 1.7, so the calcium oxide should be more. Okay? So this will give you a little bit of guideline. Then the silica fume. This is another stabilizer. So over here, the silica fume is basically the manufactured metallic silica. Is very fine, and the filter dust is called sometimes a very silica fume is very fine. So is considerably more consistent than fly ash because fly ash has different types. So unlike fly ash, it contains some unburned carbon and CaO. Unburned carbon is not good, is inactive, inert, and it's not reactive. 1 to 5% silica fume is commonly used, but we have to be careful while using this silica because it's so fine. If you inhale it, and then it will be a problem, and then the silicosis and other disease may happen. The polymer reaction is similar to fly ash, but occurs more rapidly because it's very fine. Okay, and the reaction is highly temperature dependent. Most of the cases, the reaction takes place when the temperature is more, right? So here, and the silica fume from metallic silicon manufacturers, from ferrosilicon manufacturers. So mostly the silica fume is mostly silica. It's 94 to 88%, 98. So it should be 94 to 98% should be, and then 86 to 90%. Mostly the silica. The calcium is very less. So everything is very less except the silica. Okay. Again, stabilizer types, a wide variety of material. You can use it, as I mentioned already, the Portland cement, lime, asphalt, chemicals, salt, and other techniques. So we just talked about only few. And how selecting a stabilizer type depends on a number of factors. You need to see the particle size distribution. We need to see the plasticity index. We need to see the availability of the material, of the cost of the stabilizer. We need to see the appropriate construction equipment and the climate. So a lot of things you need to check, and you need to choose that what type of admixture of stabilizer you need to use. So these are some guideline, formation of hydration products over time. So obviously the stiffness is going to increase, setting, solidification, hardening is strength gain. So what is happening over here in the clay particles of water, if we add ordinary Portland cement or slag, so what is basically the reaction is polymer reaction takes place, hydration takes place, alkali activation takes place, and final product you see here, calcium silicate hydrate or calcium aluminate hydrate or calcium CaSH, calcium aluminate silicate hydrate. These are the few things is forming. Also over here in hydration products, calcium silicate hydrate. So basically, these are the reaction product is formed. And how do you know what type of mineral is formed? So you need to do the X-ray diffraction analysis. So you pass the X-ray and then see how much is the intensity, and you need to find out that the 2 theta using the Bragg's law, n lambda is equal to 2d sine theta. From there, you can find out how much is the 2 theta and then what peaks are formed. So this is fixed for a particular mineral. So you need to know either JCPDS search match program. So you can find out that for these 2 theta, what are the minerals? So you can find out from there, and then you know what mineral exactly. So, and then also most of the time we use the 3 strong peak, and then also you can identify the minerals using manually. Also, there is if you know the despacing, if you know the 2 theta, manually also you can find out that what type of mineral is formed. This is another guideline also, Anberg and Justin. So this is you see the binder, quick lime, cement, lime, or slag. So what is happening ultimately, is different reactions, hydration reactions, alkali activation, pozzolanic reactions takes place, and ultimately it is forming the calcium aluminate silicate hydrate or calcium silicate hydrate or calcium aluminate hydrate or calcium silicate hydrate over here. Calcium, this is ettringite form, and calcium aluminate. So these are a few different. So ettringite or monosulfate aluminate or trisulfate or monosulfate aluminate. So over here. Then so I'm going to talk about that maybe in the next class. pH of the pore fluid is very important. You see the pH is increased when you use lime or cement. So alkali-acidic reactions, the reaction then it is much more reactive. Water content is important. Curing condition, temperature is important. Curing time is important. That's why with time the strength gain. So 7 days, 14 days, 28 days, 90 days. If you study for long term. Humidity is important, and the wetting, drying, and freezing time. So obviously, you check the durability. Mixing conditions. So how we are mixing the salts? Using different types of mixing blades. There are different types. Degree of mixing, how much time you are spending for mixing. Sometimes even if you wait too much of time, then it will be a problem also, because the mellowing time should be, it should not reach that when the reaction already started, So, and then time of mixing and remixing, and then how much quantity of mixing water you need to do. So again, all these things you need to check before you go to the actual site for field mixing, So you need to do the lab test first, and then go to the site and do for the field mixing. And again, as I mentioned, there's the shallow mixing and the deep mixing also. So this is Cardin et al. 1976. They have a different classification. What type of stabilizer are you going to use? So depending on the particle size, right? So less than 200, that is 75 micron, 25, and the plasticity index less than 10 and 20. So you can use either cement or lime. If at-arbag limit also you need to check, the liquid limit test mostly. And if you see that the particle size distribution percentage passing more than that, then obviously and plasticity index of the index is 10, less than 30, more than 10, less than 30. So depending on the situation, and you can easily calculate. You have an idea that how much what stabilizer is more suitable. So again, as I mentioned, that the cement is good for all type of soil. Only thing is, but more suitable for granular type of soil, sand and gravel. For clay, you need to add more quantity, and then the cost will go up, right? Lime is again, you need to use the optimum lime content or lime fixation point. First, you need to determine and then use that. So 6 to 9 or 10% maximum. If you use more lime, the strength will go down. For fly ash and GGBS and other combinations, so we need to do test, and then only you will know exactly how much, what is optimum value. Okay? You need to do a lot of trial and error. Then U.S. Army Corps of Engineers, they have there are area that like this type of different area for area 1A, 1B, 1C, area 2A, and 2A, 2C, and 2B, and area 3. There are area 2A, 2B, 2C, and 3C. There are different demarcation and major soil groups. So basically, the sand, gravel, and fine grained soils over here, and you can easily find out. So 1A is the area is basically SWSP. So basically, this is well-graded sand or poorly-graded sand over here. 1B is a mix, dual classification over here. You can see, and 1C is a silty sand or clay sand or silty sand and clay sand mixture. So that is, so basically you see the 1A is more gravel, correct? Sand and gravel. So here is a more granular type of soil, and then you can use different type of whatever stabilizer you can use over here. SP, the bitumen or Portland cement or lime cement fly ash. And if this is like silty sand or clay sand, you need to use the Portland cement, lime, and lime cement. So this will give you an idea depending on the plasticity index and the particle size division. So whether it is well graded or poorly graded, and easily you can find out from there. And what type of stabilizer. So again, these will give you just guidelines. So you need to do the actual test for a particular type of soil, what type of stabilizer is more suitable. So this will give you a range and idea, but you need to do the actual test to find out. So this is again for the area 2A, 2B, 2C. So all these things are mentioned over here. So 1A, 1B, 2A, 2A, 2B, and 2C. So all these things are mentioned over here. And then which one is bitumen we can use? You can use Portland cement, you can use lime cement fly ash. 2B, you can use like a bitumen, Portland cement, lime with lime cement fly ash. So again, depending on the plasticity index and depending on the particle size distribution. And the area 3, again, this is for mostly the clay, the high compressible clay or low compressible clay, or highly compressible silt or low compressible silt or highly organic soil. So again, you need to use the Portland cement. Or if it is like this, highly compressible, low compressible clay, then you need to use the lime. For organic soil, it's different thing. Again, we'll talk more about that. The organic soil and peat soil is much more challenging because it has fibers, it is acidic, it is too much of water content, and to stabilize this type of soil is much more challenging. So I'm not going to go here. National Lime Association. So lime content generally increase, as I already mentioned, the lime fixation point you need to check, and sometimes we can increase. First, you increase little bit of lime and just modify the lime so that modify the clay, and then you add some more lime just for the reaction. Okay, so and as I mentioned, there is a Dunlop chart to find out if you want to design a pavement, depending on the how much the cover material you need to use. Soil bituminous reactions, obviously the bitumen generally used for the pavement. Basic principle of this is waterproofing or binding. By waterproofing, inherent strength and other properties could be retained. most commonly used material, the cardpack or emulsion, and a layer can be used for the subbase or base coats for all the roads, okay, for embankment. So basically, selecting the correct stabilizing agent, there are a few things you need to check. Particle size division, as I mentioned in the table earlier. We need to check the particle size division. We need to check the Atterberg limit. So two things you need to check, and then also there is a figure over here. So this figure it will guideline of this. So based on that, so basically the particle size division you need to check. So basically, what did you do? Initial guidance, insulating stabilizer, and then also you need to check the climate and drainage. So also you need to check the climate and drainage. In the wetter areas, moisture content prevents the material. So in that case, cementitious binder usually preferred. Lime is suitable for, as I repeatedly, cohesive soil, particularly when it's initial agent or dry out the material. So that is also, so that is not stabilizer, it acts as a modifier. Using emulsion in cold, dry climate required using cement and lime facilitated moisture removal from the emulsion between the stabilizing process. So these tables will give you a guideline again, plasticity index and the particle size division when there's 25% passing more than 200 number of sieve, less than 200 number of sieves. So these blocks, so basically is here, the dark light brown is the most suitable, usually suitable. If it is a black dot, black color, this is not doubtful, and this white is not suitable at all. So basically, you see here for the line, just for example, this is the plasticity index is less than 10, and more than 25 is passing 75 over here. So that's doubtful, right? So this is more granular type of soil, right? So when you go on this side, it's much better. Okay. So and then here, if the plasticity is increased, the liquid limit is more. So obviously in that case, that is suitable also. Okay. So depending, so this will give you an guideline from the particle size division, and then the plasticity index, that is liquid limit minus plastic limit. Also, the Texas DOT, they also have that similar type. Sieve analysis, the basis is sieve analysis and Atterberg limit test. Less than 25% passing 200 sieve and plasticity index is similar type of chart you have seen. So they used, like if it is less than like this, so you can use cement and fly ash or asphalt or lime. Cement, lime, fly ash, or combinations. So these are the different, like a guideline. Again, I'm telling you need to do the test, actual test, and then find out how much is optimum quantity. Okay. So these are the different guidelines. So now also when you're doing this test, you need to find out that the different Proctor test, obviously. And then sometimes when you use lime, you see lime 0%. If you use lime, so density is decreased. Okay. So it's not that the density all the time will increase, because when immediately density will decrease, it depends on the specific gravity of the sample. So if the specific gravity of the lime is lower than the specific gravity, again, gamma D is equal to specific gravity gamma W by 1 plus E. So from there you can easily calculate. So basically sometimes it is density is decreased, but with the polygenetic reaction later on, the UCS value is going to increase. So two things. One is density, how the density is decreased, and then also different type of material. So if you use sometimes GGBS or other material when the specific gravity is higher, in that case, if you add like a density is going to increase also. So depending on what type of material you're going to use, it depends on the specific gravity of the material. Sometimes the fly ash is specific gravity is lower. When you use fly ash, generally density is going to also decrease. But when you reaction takes place, then again the strength will go up, the UCS strength. So suitability, again, you need to check. The lime works best for clay, especially though with moderate high plasticity, less than 15, plasticity index less than 15. Due to lack of aluminous and silica in silt, granular polymerization do not take place. Therefore, lime does not work well for the material. So granular material is not good. In order to select silt and granular materials, so polygenetic admixtures like fly ash need to be added in addition to lime. And then also the little suggested that UCDS classification, what type of stabilizer is good. And again, also, you need to check that the sulfate concentration, if it is more than 7,000 to 800 ppm, lime can be used. With sulfate concentration. But as I mentioned, if you use cement, a lot of sulfur, then it is not good. Okay? But lime can be used up to that percentage. It's less than this. So again, minimum UCS strength. There are several criteria: 7-day strength, 28-day strength, UCS strength for the base course, and then this is in PSI, pound per square inch. Flexible base course. Sub base course is lower bottom. The base sub base course, base course, and surface course. So sub base, most of the time, the native soil is below this base sub base course basically. So and then we need to stabilize or improve. For the rigid pavement, obviously the flexible pavement is the asphalt one. The rigid pavement is basically the concrete pavement, and the strength, you need more strength compared to that for the flexible one. Okay, so Portland available as I mentioned. So there are, you see here, type 1 cement, type 2 cement, type 3 cement, and then these days, depending on your requirement, you can use that. Sometimes there are sulfur resistant cement. Sometimes we need quick setting cement. Also, you can use, and then also if you need the strength very quick, you can use like calcium sulfaluminate cement also. For screening test of organic matter and sulfate. So again, if most of the soil, if there is an organic matter, we need to generally get rid of that organic matter and also sulfate. Tests are generally detected for these materials should be conducted if there is a presence of suspect. So we need to do that. And also pH. We need to do the test for pH. 10:1 for the soil and then and cement. 15 minutes after mixing, and if you see where it's 12 or more. So again, like Eddy's and Grimm's method you mentioned for the lime, the same thing also you can use it. For the sulfate, sometimes because of attringite formations, there is some problem. The sulfate clay reaction caused deterioration of the fine-grained soil because of the attringite. So we need to test that clay soil first. How much is the maximum sulfate content is there? And then also the use of cement in fine-grained soil contains more than 1% sulfate should be avoided. So if the sulfate content is more than some ppm level is fine. If it's more than 1% sulfate is there, then don't use cement. Okay. There are some guidelines also there for how much quantity of design cement content you need to use. So 100 times A is equal to 100 times B times C. So depending on B is equal to percentage passing, number 40 C we express in decimal. C is the percentage of cement required to obtain the PI minus 40%, number 40 material expression. So again, this will give you some guidelines. Earlier you have seen, this is ASTM 425, 423 and 425. So you can find out how much is the optimum quantity of cement. Most of the time, people use here in Illinois, depending on the type of clay, is 5 to 10% maximum. Because more cement, you get more strength, and then obviously the cost will go up. So that's the reason people don't use too much of cement. This will give you some guideline, as I mentioned, like if you use that the well-graded gravel and sand as per USCS classification. These are all USCS symbols, already. This is 5%. You can use if it's well graded, so 5% to 6%. If it's poorly graded, is a little bit more. So well graded soil is, the soil has all the different size particles, right? So we need that. The compaction will be good, strength will be good, and then it's poorly graded, so we need a little bit more. If it is a silty type soil, silty gravel, silty sand, clay gravel, all this, and the dual classification, the percentage finer. 7 to 12, more than 5 and less than 12. So then there's a dual classification system. So in that case, it's 7%. And then that highly compressible soil or silt and clay. So then you need to use a little bit more, 10 to 12%. So depending on the, again, this will give you a guideline only. Okay? So, and yeah, I think that's all for, all right. Anyone has any question? So I have not explained much on this other stabilizer, like in much more detail on the reactions. I just mentioned the very basic thing, what is happening, what are the tests, chemical combination you need to do, and then also basically the particle size and the liquid limit test, you will know what type of, and then you see the chart, you can easily calculate pH test you need to do, and then cement and lime and fly ash. If it is a polygeneric material, so you need to add a little bit of lime and fly ash, lime and cement, then the reaction is going to occur. And then, you need to do several trial and error tests and find out the optimum. Only thing is the lime is, you need to have a lime fixation point. More lime is not good. So more lime, the strength will go down. Okay. 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 All right. Well, regarding knowledge, yeah, I can read now. I can see, yeah. Expansion of clay having higher processing rate, the addition of lime leads to higher moisture content compared to the untreated. Expensive clay. Yeah, I mean, if it is expensive soil, so again, you need to be, so again, if you use lime, so obviously lime, it will increase. So again, what type of test you're going to do, right? So if you do expansive index test or any other test, so first as I mentioned, the density, as I've seen the standard Proctor graph, where the lime is going to decrease, is basically optimum moisture content is increased basically. But when you prepare the soil sample, with time, it will be fine. Sometimes the pure lime is not going to help. So sometimes you need to add some lime, some other stabilizer also. Okay, so it depends. And then for durability aspect of GGBS, so durability again, I'll show you some results with some different mixture of so durability aspect is basically what you need to do. You prepare a sample and then you do accelerated either freezing, thawing, or wetting drying and see what is happening. Basically, you need to see the volume change, there is a loss of mass, all these things you need to check. And then after how many repeated cycle, and then you can determine. Okay, so you cannot say that. Yeah, you need to do the test, and then only you can say how durable is that. Okay, does it make sense? Okay. 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 All right. Okay. Bye.
Recording stopped.
And like how much time I have for this one? So, and that's all for the day, correct? Okay, okay. All right. So again, I hope everyone joined, but let me start. All right. So welcome back again. So now I'm going to talk about like a non-traditional stabilizer, like a geopolymer. So these are the slides, some of the slides I just took presented in IGC, recent last IGC, anyone, if someone was present there, so they'll be, listening to the same thing. But I'm just going to talk about little stabilization. Geopolymer stabilized highly subgrade using industrial byproduct. So talk about the background and then some problem, and then what are the experiment we did, and some statistical results and the sustainability assessment. And also it is not there in sustainability assessment for maybe the next early, but I'm going to explain that and the conclusions. So as I mentioned, all these methods you already explained, densification, consolidation. So this is the chemical modification in the geopolymer salt stabilization we're going to talk. And so here now, why are you using geopolymers? What is the problem first? So people most of the time you use the road condition is not very good. Even people are using cement, so that produces million tons of CO2. And then also here in this particular experiment, we did a lime sludge, that is an industrial byproduct from the water treatment plant. We use GGBS from the steel industry. We use coal ash from the thermal power plant. Okay? So here, so basically these are the experimental plants. So we used EPK clay. So this is a commercially available clay. And then you use fly ash, lime sludge, and GGBS. And then you use different combinations. And so because this fly ash was class F, so we use that fly ash with lime ash and fly ash with GGBS just to make it more pozzolanic. And then we did different geotechnical properties, physical properties, and then we did the structural analysis, and also we did sustainability analysis. So now the thing is, for geopolymer, I'm going to talk about that. So geopolymer, mostly when you add that different material, and then pozzolanic material, and then also the sodium hydroxide and sodium silicate. These are the two things you need to add, basically, and we need to increase the temperature. Basically, the reaction should be, the reaction takes place at high temperature. So that is the little bit of practical problem for geopolymer. But here we just check with, what is happening when you use like a normal temperature, ordinary temperature, that is 23 degree, and compared to the 70 degree, generally use 65 to 70 degree Celsius for this geopolymer. Okay. And then also we check like which one is better, whether fly ash lime sludge is better or fly ash GGBS is better. So both are waste material. So that is the idea, is basically use that waste material instead of using cement or lime, all this waste material to stabilize the soil. So geopolymer, as I mentioned, geopolymer inorganic molecule synthesized by an activated polykondensation reactions. So basically, you see the silica, alumina, the silica, oxygen, alumina. These are the critical structures. Basically, the Zhang et al. 2010, the chemical structures of geopolymer is Mn, silica, SiO2, Z, Al2, AlO2, 2, and then M. So M is the alkali cation, such as potassium. It can be potassium, it can be sodium. That balances the negative charges for the aluminium. And N is the degree of polykondensation. It can change. We can change the alkali to silica and alumina molar ratio, ranging from 1 to 15. Okay. So most of the time, so that, as I mentioned, so the silica and alumina, you can change, and also you need to use the alkali, mostly either sodium hydroxide or potassium hydroxide and the sodium silicate. So first thing is the first phase is dissolution of amorphous silicate material. So silica, so soil is clay is having mostly the silica and alumina iron, right? So silica and alumina is dissolved by this sodium hydroxide, and sodium silicate. And then the reaction takes place, and then the Foley condensation of the dissolved species takes place, and then the geopolymer form. So over here you see the step one, chemical attack, then dissolution takes place, gelation takes place, polymerization takes place, and the growth, and then basically the geopolymer is formed. So people already studied the studies for geopolymer soil separations. Over here, you can see the UCS strength, how the UCS strength grain after 28 days. Over here is 110 to 124 ESI. And this is the reaction, basically the clay particles and the silt particle and the precursor when we added. So what is the reaction? So basically all the voids over here, this was voids, so all the voids with the reacted product or synthesis geopolymer. So this is some of the another results also that people have done. The compressive strength at 7 day, 28 days. So 28 strength is much more. Some cases, the 7-day curing is much more than 28 days for the different combinations. So as I mentioned, so you need to do different tests and then find out which one is that optimum percentage. So here for the current study, basically one of my PhD students, he did. So the class A fly ash, we use GGBS and lime sludge. And then we use alkali activators, sodium hydroxide and sodium silicate, not the potassium hydroxide, sodium hydroxide, sodium silicate. And then we did the experiment for normal temperature, that is room temperature around 23 degrees Celsius, and then elevated temperature basically for 75 degrees. So and then also we did the sustainability assessment. So again, the life cycle cost assessment. So we use that embodied energy, we use the environmental impact, we use the life cycle costing, all these things, and then 3 index find out the that sustainability index, resource consumption index, environmental impact index, and then socioeconomic impact index. Again, we used the data from the standard data we used, but there are different softwares you can use, SEMA Pro and other, to calculate all the sustainability index. So here, what we did mostly, we mixed with EPK clay with different stabilizer, as I mentioned, lime sludge, GGBS, and fly ash, and we did the basic test, specific gravity test, particle size, liquid limit, XRF. And also we did that UCS test, we did LCA test, and then we did FTIR and X-ray diffraction, all these different tests to check what is forming inside that after the stabilization. Okay, so these are the different combination of tests we used, and over here. So all samples are cured at 7 and 28 days, and amount of binder percentage is basically calculated based on the dry weight of the sample. And then also we used the control test without anything, that is 100% EPK clay. And then we used EPK clay plus 5% fly ash, 5% lime sludge, and GP is basically the geopolymer. So we added that sodium hydroxide and sodium silicate solution. So, and then that 5% fly ash, 5% lime sludge. Second one, M3 is basically EPK clay plus 10% lime sludge, 10% fly ash, and geopolymer. Then we use like a 10, 15, 20, same thing for 10, 15, 20 for lime sludge. And we use that only, the lime sludge percentage you changed, So basically we used the only lime sludge and geopolymer. We used fly ash plus lime sludge with geopolymers, and we used fly ash plus geopolymer, GGBS and geopolymer, also fly ash plus geopolymer. So different combination, we check which one is more suitable. Okay. So, and then I'm not going to go in detail the procedure. So basically the sodium hydroxide, this is very important. So in this case, we use like a sodium hydroxide and sodium silicate ratio is 1.5. And then the ratio of this the total weight to the sodium ratio of the ash to alkaline liquid, which is total weight of the sodium silicate solution and the sodium hydroxide solution maintained 0.55. Just for example, this is like a water to cement ratio in concrete. So we maintain that 0.55, and the compaction is done in 3 years. And then for ECS strain, these are the rate of strain 0.05 inch per minute. And then we did test for 23 degrees Celsius. There's the ambient conditions, and we use that 70 degrees Celsius. And test has been done for the 7 days and 28 days. And the moisture content of the cross samples recorded after 28 hours. 24 hours. These are the particle size division graph for EPK clay, lime sludge, fly ash, and GGBS. You see the GGBS is more coarser, and then there's the lime sludge, and then fly ash is more uniform, and then EPK clay. These are the properties of the EPK clay. The specific gravity is 2.61. Liquid limit is 72.7440. Plasticity index is plasticity is 34.9. Maximum dye density is 1109 kg per meter cube. And then optimum moisture content is 33%. It's quite high. So as per USCS classification, this is treated as high plastic silt. So properties of EPK clay. So mostly you see here, mostly the silica is a major component. Calcium is 0.18%. So EPK clay is basically just 1:1 clay. So you know that the silica, alumina, and so silica tetrahedra, alumina octahedra, how they are arranged. So 1:1 or 2:1. These are the chemical compositions of the fly ash, lime sludge, and GGBS. So you see the first column is the fly ash. So here calcium is 3.8%, is very less. So this is class F. And then if you add these first three, silica, alumina, iron, it is more than 70. So that is class F. Lime sludge over here, it is a byproduct from the water treatment plant. The calcium carbonate, calcium oxide content is 51%. That is good. And then GGBS is also 42%. The calcium. So calcium is the one we needed, for binding. So here, this is the test results for stress strain behavior of 7 days when we combine with fly ash and lime sludge. But it is in MPa. For EPK clay is lower one, and you see here. The strength is going up with different percentage of fly ash and lime sludge combinations. And so this is the figure B is the same test, same combinations, but with high temperature. This is 23 degrees Celsius. This is 70 degrees Celsius. So geopolymer. So geopolymer is basically the reaction is not going to occur unless you elevate the temperature. So the problem is in real life and practical applications. How we're going to increase the temperature at the site. So that's why we tried both method and see what is happening. So how much is the strength increased with temperature increase, and then how much is the ambient situation. So this is for EPK clay with fly ash and lime sludge. This is the one, this results is basically with fly ash and lime sludge combined. Okay, fly ash and lime sludge combined at the same train. After 28 days, the elevated temperature shows more strain compared to the normal temperature. But this is also quite high strain that you see a 5% fly ash and lime sludge is 4 MPa is quite a strength. Then here, in this case, this is we tried with temperature a little bit increase, instead of ambient temperature, we increase 35 degrees Celsius and see how much is the strength gain. And we see that, at 70 degrees, the strength was at 28 days, almost 6 MPa. So here, 28 days, the strength is around 4 MPa. It's not that bad. But compared to the ambient one, it's a little bit increased. compared to the ambient one. Okay. And then this is the results for 28 days strength. Again, fly ash with GGBS. Earlier when the fly ash with lime sludge, now fly ash with GGBS. So again, elevated temperature shows higher strength compared to the ambient temperature. This is overall, you can see here the effect of fly ash and lime sludge. What is happening in the 7 days and 14 days. So most of the time, the 7-day strength is lower and 28 days is higher. Everywhere you can see that. But some cases fly ash and lime sludge combinations at elevated temperature, 7-day curing is more than this 28-day curing. Okay. So this is again from the stress strain graph. We calculated the modulus, plastic modulus, and we calculated that for different temperatures and different combinations. So most of the cases, modulus rigidity in the slope of that stress strain graph. So it's more means it can take more load, more stiffer, and then the 70 degrees Celsius in the higher temperature, again, it shows higher E value, modulus of elasticity. And then for the same thing for GGBS and fly ash content and the 7 days curing and 28 days curing, what is happening for the UCS test results. So most of the time it is like is increasing from the original 1 to 5, 10, 15 is almost the same. It's not much change. So here 5% even giving more results than 15, 20, and 10, 15, and 20. So again, as I mentioned earlier, so we need to really do that test and then find out for which one is optimum for any soil separations study. So this is the modulus of elastic material for different combinations of the EPK clay or fly ash or GGBS mixture for elevated temperature. And the first two one is the normal temperature. Bottom one is the elevated temperature. What are the values of UCS values? E values and the failure strain. And then how much is the volumetric strain? Also, we calculated over here for the lime sludge and then lime sludge fly ash. So lime sludge fly ash, when mixed with that, obviously the volumetric strain is decreased. So here, these are the failure pattern, how it looks like, for the different soils. So most of the cases, when the soil is very stiff, so the sample behaves like a brittle type of failure. And when the soil is, so that's the reason people, so if the soil feels like a brittle, then it is a problem. The failure is sudden or catastrophic. So that's the reason a lot of people are using like fiber type of material so that it can take some load or it will be more resilient. So this is the statistical analysis has been conducted using ANOVA, UCS, Young modulus, and failure strain, and then p-value calculated is less than 0.5. At least one of the population means in different from others, and then so this is the values for the different soil sample, as I mentioned earlier, M2, M3, M4, and calculated the UCS, the failure strain, and modulus of plastic value. And then, so these are, so obviously the influence of the curing we conducted, and influence of the temperature we conducted, so all these different things. And then, so also for different combinations we conducted. And finally, from the statistical analysis, the regression model. So we use the UCS test. You are interested in UCS test, the function of fly ash, lime sludge, unit weight, dry unit weight, bulk unit weight, and the curing temperature and the curing time. Okay. So and then we develop this equation, and then from here you can use that UCS strength is 0.081 times how much the percentage you use, the lime sludge unit weight, bulk unit weight, the temperature, curing time, and the curing days. So you can use this equation to calculate and this using the statistical model. So now what is happening in this scanning electron microscope for studies, you see that lime sludge and fly ash. So most of the time, is over here, the fly ash. This is the original sample. The fly ash particles, the pockets of the voids. There are lime sludge, looks like this. When you added the mixture, so like this one, you see the EPK 5% fly ash and 5% lime sludge. There are, the more agglomeration takes place, the population takes place, and then there is less voids inside the stabilized soil. That's why the strength is increased. So we need to calculate that how much is the silica alumina ratio, silica alumina silica calcium ratio, and the sodium. So all these things you need to calculate. But again, this is EDAX. From there, you can find out what are the different chemical composition. But this is not going to, this will give you an idea. But only thing is how many minerals, how many chemicals are there. So they combine it to make it 100%. So that will not give you a quantitative one, but this will give you just qualitative chemical compositions. So these are different combinations. So what is happening over here? So it's much more condensed for the geopolymer sample from these microstructures. Okay. So and then that's the reason the strength is increased. So so again, these are some of the things as I mentioned. So obviously we need to find out what are the mineral forms. So either sodium aluminate silicate hydrate or calcium aluminate silicate hydrates, all these different mineral forms. And then also that most of the time is 23 degrees Celsius, 70 degrees Celsius is much better compared to the 25, 23 degrees Celsius or room temperature. So these are again some of the pictures, micrograph of fly ash versus lime sludge. And you see for EPK clay, only 28 days, nothing. So there's a lot of voids, but with this different type of stabilizer, we can see that the reaction is better, less void, samples are more condensed because of these different mineral forms and because of the geopolymer. So in the sustainability index, I'm just going to tell that these are different index we calculated finally using this greenhouse gas, then an inventory of the carbon and energy database. We use that, and then we calculated all these different embodied energy for the lime, fly ash, and GGBS. And then we calculated that the different, I'm just going to go here, the final index, sustainability index. So we'll be getting a graph like this, and that add a chart. So most of the time, you see the original one, the method A is using lime. So this dotted one. Method B, the green one, uses 15% fly ash and 15% lime sludge. Method C uses 15% fly ash and 15% GGBS. So the more area means you are using more energy. So basically here in this case, method B, that is fly ash, 15% and fly ash and 15% lime sludge is much more sustainable for this case. Okay. So again, you need to calculate all this weighted index and stuff. We can use that from the different data from the, as I mentioned, the sources, and you can calculate all these different index, the resource consumption, environmental impact, and socio-economic impact. And finally, you got this graph like this. And then from there, you have an idea what type of stabilizer is most suitable from the sustainability point of view. And then from here, conclusion from the study is basically the lime, fly ash, and lime sludge geopolymer is having more successful use to improve the geotechnical properties. There is no record of using fly ash geopolymer-based geopolymer. So this is, people have not done this earlier. And then the failure pattern of untreated is bulky nature, but when you use that, the behavior is more stiff. And then we have seen that the scanning electron microscope, that the curing of GGBS stabilization samples under both 23 degree and 27 degree shown positive results. To higher the temperature, the strength is more. And also we did some tests like a 35 degree, even we checked substantial increase in the strength. And again, as I mentioned, the sustainability index point of view, that lower sustainability index indicates the more sustainable alternative. So as I mentioned from this data chart area. And then also we use that the ANOVA for the statistical analysis, the Young modulus, bulk density, and failure strain. And the correlation was R-square value is 0.7, is quite good. And then you can use that equation for to estimate that UCS value. We try to estimate the UCS value from there. Okay. And obviously, we have not done the studies only OPC. So obviously, if you use that OPC, then you can really compare how much is the strength for fly ash and lime sludge or fly ash with GGBS and compared to the OPC or lime. Okay. So again, the sustainability index, as if we are used that here we use that lime as a reference when you calculate the sustainability index. So we calculate how much is the energy required in compared to the lime stabilized soil, and then when you use that fly ash plus lime, fly ash plus GGBS. So I think that is the one I just want to tell quickly. That is the one basically, as I mentioned, the geopolymer stabilized soil. So this one is durability. You know, I'm just talking about a little bit of durability. So here, so durability also, this is one of my graduate students' work. So he studied a lot of studies. So this paper is going to publish in Transportation Geotechnical. So here he used the fly ash and GGBS also for geopolymer for high plastic clay. So basically, you know, I'm not going to talk about that basically. So why use geopolymer? The idea is, so we are not using conventional material like a cement or lime. That production itself is generate a lot of CO2. So geopolymer is eco-friendly. And then here in these studies, what we did, like most of the cases, the geopolymer, we use the mixing process, the wet method. So over here, a traditional geopolymer, so we use fly ash and geopolymer soil sample, and then we use that alkali precursor, sodium hydroxide and sodium silicate solution. And when you add water in sodium hydroxide, it generates a lot of heats. And then sodium silicate, you mix this solution, keep it overnight, and the next day you add with the, you know, in the mix with the fly ash and GGBS and soil together. Okay, and then the geopolymer is going to form basically when you keep it either natural or maybe, you know, inside the oven for 70 degrees Celsius. So this is traditional method. So we tried, because when you add water into the NaOH, you know, it generates a lot of heat, you know. So why not we use that heat, you know, to without increasing the temperature of 70 degrees. So see what happens. So we use fly ash, GGBS, water and sample, and we grinded that NaOH in powder form, and then we add it together, everything together, okay, and mix it and cure for normal temperature. So normal temperature, so you see just normal temperature, what is happening, okay. So we are not using elevated temperatures, and then see what is happening. So using just using the heat from NaOH, okay, when we add water into that. So here, so we use some clay. This is not the EPK clay like the previous studies we mentioned, the commercially available. This is actual clay, and then and then we use the fly ash and GGBS, and then that we mixed with different percentage. We mixed with the dry mixing approach. We mixed the wet mixing approach. Compared with the wet mixing approach, and then we did that the wetting, drying, and freezing thawing durability test, and also we did that ACM test. So basically, you see, this is clay. This is a clay soil. This is the fly ash, and this is GGBS. Here, I just want to mention over here, this is also class A fly ash, obviously. So here, the sodium hydroxide, we use 10 molar. So again, various studies are there. They're used from 5 molar to even 20 molar. So based on the studies, the literature, So we use the 10 molar, NaOH, and then we use the sodium silicate also. So these are the combination we used for these studies. Basically, we used pure clay. We used 5% fly ash and 5% granulated blast furnace slag, plus geopolymer. We are talking about the geopolymer is basically we are using sodium hydroxide and sodium silicate. And then the second one we tried with clay with 10% fly ash and 10% GGBS plus geopolymer. And then the third one is 15% fly ash, 15% GGBS geopolymer, and 20% fly ash, 20% GGBS and geopolymer. So different combination you use and to see what is happening. Okay. So basically, as I mentioned, the wet mixing method, and then how you compare with the wet mixing method also what is happening with the studies. Okay. So here, these are the different tests we use. So we use, as I mentioned, that clay is not CAS, it should be C. So clay is 43% clay, 52% silt. Fly ash is mostly the silt, and then GGBS is 41% silt and 9% clay. This is the particle size distribution graph. And then the chemical composition is very important, as I mentioned earlier. The chemical composition of fly ash, GGBS, and blast furnace slags. Over here this fly ash is used over here is class C. Is the calcium is 22%. And then specific gravity of the clay is 2.65, liquid limit is 60, and plasticity index is 34. This is for experimental test for, as I mentioned, for design mix. I think I've seen this. So this is the combination for wetting drying and freezing thawing. So meaning WD0 means basically is just pure clay. It's nothing added. Freezing thawing also FT is freezing thawing 0% only for the clay. If we have 5% means WD5 means 5% fly ash, 5% GGBS and geopolymer. And then it is wetting drying is WD and FT is for freezing thawing. These are the combinations we used and the notation. And then this is the behavior, okay, of the stress strain behavior. Over here, you can see the clay is at the bottom without anything. And then this is clay with, so 20% fly ash and 20% GGBS is the highest one. Okay. Then this is for the 28-day strength, stress strain behavior. So geopolymer stabilized clay soil at 28-day strength again is the clay. And then you see here like a standard modified Proctor test type of behavior. You see the more stiffness, the modulus of plasticity is also increases. And then this is C, and then this is the one you see here 20% fly ash and 20% GGBS for 28 days. This is the UCS strength again for 7 days and 28 days. So 7 days and 28 days, you see not much of difference, in the strength, 7 days and 28 days. You see here some of the cases, some combination is almost the same value. It's not much of difference, Here in these combinations, 15% fly ash, 15% GGBS, a little bit more. 20% is a little bit more, but not much difference. Okay. UCS strength over here. So this is for different combinations. You can see the values of also here, and then the modulus of plasticity, how the modulus of plasticity is changing for 28 days. So 7 days and 28 days. So this is first column is the 7 days, is 28 days. This one is 7 days and 28 days. Not much difference. This is also not much difference, as I mentioned earlier. And then also how the UCS E value is, elastic modulus is also going to change with different combinations. So C is the pure clay, and this is fly ash plus GGBS, 5%, 10%, 15%, and 20% fly ash, 20% GGBS. So then this is the failure pattern, how it looks like. So most of the cases, if it is pure stabilized soils, and stabilized also, we can find out, like in most of the cases, it is, if it is more stiffer, it's more brittle failure type, So now for this wetting and drying test, so you see the untreated samples, it dissolves immediately. Okay, these are the samples you prepared, and then I'm not going to explain how to do that. So most of the time, there is a standard procedure, ASTM. So you need to prepare the sample, and then you need to insert into the water, and then keep it for certain time, and then take out. And then when the sample is there, it's a dry it, and then you brush it using a wire brush, and then see how much is the loss. So from there, you can find out how much is the loss, how much is the volume change, all these things you can calculate from there. And then same thing you do when you keep it in the freezer also, the freeze, and then you take out, and then also do how much is the loss or volume change and stuff. So here, untreated sample collapses immediately, it's like this. And these are the samples for the wetting, drying, and then after one cycle, it's almost intact. This is after 2 cycle. So here we use 2 identical samples for each test, and this is sample 2 after 3 cycles. This is only 1 sample is remaining, so other is not very good. Sample 2 is after 4 cycle. Same thing for this is 5%. This is 5% fly ash, correct? So WD is basically 5% fly ash and 5% GGBS, and with geopolymer. So this one is WD10, means in the notation you mentioned 5% 10% fly ash, 10% GGBS, and geopolymer. So this is, you see, with the geopolymer. So 1 cycle is survived, 4 cycle, all these survived, 7 cycle, and 12 cycle, only 2 samples are survived over here. So basically this is a durability study. So you see it's much more durable when you use geopolymer. So this is again some of the pictures after 1 cycle, 4 cycle, again after 1 cycle, 4 cycle, after 8 cycles. So what is happening basically for the sample over here? And then if you calculate how much is the mass loss, so with wetting, drying, if the 5% is mass loss is much higher compared to the 20% WD over here, So 20% and 50% is almost the same over here, So 20%. So we need to check. So which one is the head loss is the mass loss is. So mass loss is more is not good, right? So mass loss is less is better. So So continuous increase in mass loss observed in the cycle progress, and primary due to the extinction or leaching of the particles during wetting phase. So basically how the sample is, if it is not contact in a matrix forms, it's going to leach out. So volume change, the volume loss also you can find out from the same sample for the wetting drying test. And then the bulk unit weight is not much change in the bulk unit weight, okay? And then same thing also, same soil combinations, but for freezing and freezing time thawing test. So freezing thaw effect for the first cycle. So, and then these are the different cycles for freezing thawing. You see the first cycles after first cycle. So this is the effect on freeze thaw without any stabilizer, without anything. This is the situation. The first cycle itself, this is already cracked or broken. Maybe at the joint it came out. But for freezing thawing for 5% fly ash, 5% GGBS, this is after 1 cycle. After freezing thawing of 2 cycles, 2 cycles, after 3 cycles. So this is happening. What is happening? Freezing thawing, and then also wetting, drying, and freezing thawing. So this is the situations over here. And this is not the wetting drying. This should be freezing thawing. This is also freezing thawing, but 10%. Okay, this is 5%. This is 10%. This should be freezing thawing, not wetting drying. Okay? And the mass loss over here is 5% is more mass loss, and then 10%, and then 15 and 20% is also the same. Okay? Volume change behavior or volume loss is also, you can see from this graph. Bulk unit weight also decreases progressively with each cycle, because sometimes multiple cracks store a lot of water into that. So that's the reason the unit weight is increased. So over here, this is the, as I mentioned, this is the dye mixing method used. So we used wet mixing method also earlier studies. So we compared with that dry mixing and wet mixing. What is the difference? So obviously, wet mixing is the strength is much more for the same combinations. The dry mixing is 7 days and 14 days. MPa is much less every time. For the dry mixing is every time the strength is much less compared to the wet mixing. Okay? Because the wet mixing we used only the heat from the NaOH, right? So we have not used. So maybe the mixing is not proper. In wet mixing, we use that sodium hydroxide and sodium silicate in solution, and then mixed with the clay and the stabilizer, the mixing is much more proper. Maybe here, sodium hydroxide and sodium silicate is not reacted or not mixed properly with the soil. That's the reason maybe in a dry mixing method, is the strength is much lower for exact same combinations of the soils. Although we compared with EPK clay, this is the normal clay. Okay, but just for the comparison. And then again, this is the particles, the scanning electron microscope of the pure clay. This is GGBS, this is fly ash particles, and then with 28 days, the 10% fly ash, 10% GGBS, how it looks like is much more condensed structures, with less voids. And then because of this formation of either calcium silicate hydrate or calcium silicate aluminum hydrate. And again, this is 15% fly ash and 15% GGBS. So even you see how the microstructure looks like. So much more dense structure, more dense structures. This one is that 20% fly ash and 20%. Again, you can see it's much more dense structures compared to the untreated sample. And then finally, what you have noticed that over here, that dry mixing method proves effective. 25% fly ash and GGBS geopolymer exceed the criteria. If you consider the ASTM criteria for UCS strength, that over 0.8 megapascal, then it can be used for soil stabilizer purpose. GGBS and fly ash geopolymer increases UCS strength for both 7 days and 28 days. So 28 days peak is 834 for 7 days and 967 for 28 days. So it increased like a 267 to 190% compared to the control test when you are not using anything. So 7 days and 28 days is not much of difference. The 10, 15, and 20% mix is so excellent resilience, surviving all 12 wetting and drying cycles. And then mass loss and volume loss decreased with the higher geopolymer content. And then with 20%, so the least loss. So 20% mix is the best combination. And the strength increase, as I mentioned, is 267% increase for 7 days and 190% increase for 28 days. And then for all mixes, mass and volume loss were higher than the initial cycles, followed by considerable decrease in the subsequent cycles. So geopolymers sample are effectively affected by freeze thaw. So freeze thaw, so no, I mean, for all the combinations, no samples survived after 12 cycles, whereas the for wetting drying, samples survived. So freezing thaw is more, it seems like more harsh. Mass loss and the volume increased with each freeze loss cycle due to bulking, while bulking density steadily decreased. And SEM images, it's a thick and compact microstructure because of this formation of calcium aluminate silicate hydrate or sodium aluminate silicate hydride gel. And then that's the reason, the durability is increased. And so all this, as I mentioned, so like these durability studies for anything. I mean, this is just one example I mentioned over here. And if you want to read more details, so these are the paper. These are the results I've taken from this paper, of my paper. So if you want, I can send this paper for further studies. So basically, this is basically the geopolymer. I talk about geopolymer. I talked about geopolymer, how when you mix in dry situation, that is not common. Most of the time we use in wet form. So what is going to happen? And we discussed about like a ambient temperature, and then also we discussed about the curing temperatures. What is going to happen to the strand? Okay? And then so as I mentioned, so you know how much time I have now? Anyone can tell me how much time we have? Okay. All right. So now the last topic is basically I'm going to talk about, but again, I'm not going to go and discuss in detail. So basically the ground freezing and ground heating. So mostly the ground freezing is basically is developed in 19th century. So basically what you need to do if the water table is too high, water content is there, so you just freeze the whole ground, okay, and then do the excavation and construct something on that type of soil. And there again is not a cheap method, so you can use that. When you cannot use any other method, so in that situation you need to use this. Okay. So as I mentioned, this is started in Germany. People are using it frequently here in US. I know there are some projects in New York and California also. And I just want to mention over here that in ASCE Geo Institute site, if you can go ASCE Geo Institute site, and there is a geotech tool, there you can find out a lot of information on these different ground improvement methods. And then I was involved in this ground freezing method with Joe Sopko from Ground Freezing. He's the director for that company. So we had a small project from ASCE and we did that. So please look into that. That ground freezing we created. There are a lot of information is there, different case studies, a lot of pictures. And then also mostly application for the tunnel applications, and also that the construction of drill shaft. Okay, so there are two main topic there, and then also different case studies from different countries. So this is a very nice source information of this ground freezing, and we did that last year. So hopefully everyone can see that you'll find out more information about that. The ground freezing, as I mentioned, so it can, generally is a drilling technology, freezing and drilling technology in advance, more applicable for the civil construction. So it started in 1950. Extremely difficult of the soil can be remediated with great success. So obviously, again, you can do it like a foundation shoring. You can do the coffer dam. You can do underpinning work. You can do temporary access road using soil freezing. Is more common. So you can go up to even 2,000 deep, 2,000 feet deep for the construction using freezing method. Again, it is expensive. It's not easy. So now how to freeze the ground? There are the principle of ground freezing is ground freezing process in which the in situ pore water is converted into ice. Okay, like in like the cement in concrete, right? Ice bonds soil particles together, and then imparting the strength and impermeability of the frozen soil. So, frozen soil, the ground freezing is based on the withdrawal of the heat from the soil. So you just really remove the heat and then and freeze the ground. So basically, what you need to do, you need to pipeline system, like a dewatering system. You use the pumping the water out. So a pipeline system, you just freeze the ground either using brine solution or using nitrogen, liquid nitrogen. So you use that inner pipe. the pipe into the ground, and then either brine solution. It can be closed and open source, and then freeze the ground and then do your construction. So over here, brine freezing, you see the freezing ground over here. So you use a cooler, and then you just one pipe, it will go that calcium chloride solutions, and then the lowest temperature can be achieved by minus 55 degrees Celsius. So it can be, so this is how you freeze the soil. And then this is calcium chloride, how the circulating the brine. You see over here the same supply. There's this closed system, and then you freezing the whole soil over here in this ground. Again, I'm not going to go into the interfreezing plant. Consists of the number of freezing unit, how many number of freezing units required. The same thing like dewatering technique. Several additional components like a low voltage switchgear, tank of the brine solutions, how many, and then recooling machine. So again, I just want to show you some pictures, and some of the graphs requires freezing time. So this will give you an idea how many spacing on the pipe or required freezing time is required. So depending on the water content, and also freezing time versus the distance from the freezing pipe. So again, you have a freezing pipe like an influence zone, right? The same thing also, how much is the influence zone will be when you freeze that down. So this will give you an idea that, and also how much is the the freezing pipe spacing, right? So application is, it can be temporary underpinning structures. It can be ground support to seepage control during tunneling, large open excavation, retaining structures, tunneling through the full space granular soil, sinking and lining of mine shafts. So few things, when there is a leakage of water, is there temporary cut-off wall, all these things where you need to, there's a problem with the water, you freeze the ground and then do, or when the construction is, even machinery cannot go, freeze the ground, and then the machine can go and then do your construction. So as I mentioned, it can be temporary method, it can be excavation, support for the excavation, it can be tunneling, it can be underpinning of existing structures or environmental applications. So again, these are some of the pictures you see for the tunnel. It can be for the retaining structures, for the open structures. People don't use it mostly for the shaft or retaining wall. This is how you do, like it's frozen the whole soil, the first one, and then you see just cut it, the wall support, and then cut it like in tunnel construction what you do. Only thing is, I'm just going to go in detail. I'm not going to go. So here you need to understand, if you want to read more details, like a frozen soil, that the phase diagrams here, the gas here is the water unfrozen and water is not frozen, and then water is forming ice, okay, and then the solid. So these are the few things you need to know while designing this, that how much is the unit weight or density will be. Again, the specific gravity, gamma W by 1 plus E plus here, it is a little bit different than conventional one, okay? And then if you use liquid nitrogen, so this is how you do, like a supply the liquid nitrogen and then come out, and then the whole soil is going to freeze, okay? And it can go up to minus 196 degrees Celsius when you are using liquid nitrogen compared to the calcium chloride or brine solution. So I'm not going to go in detail. So here, this is some of the pictures. Again, ground freezing a technique extremely used for ground control, groundwater control, and excavation support for the underground construction. So underground construction, you just freeze the whole ground, so it's not going to collapse. So that's the idea. So again, as I mentioned, so you can find out several pictures from Geotech tools. Okay. Similar principles, I'm not going to go in detail over here. So this is how it looks like. You see there is freezing pipe over here, the header and riser types, and then freeze the whole soil, and then do the excavation, at the middle. Okay. So that's how it's easy to construct. But again, this is expensive. So you have to keep this running while doing this excavation, until you put a cover material while the excavation is done. Freezing process, there are indirect process or direct process. I'm going to go in detail over here. And then So this is some of the freezing methods. I'm just going to go here. Mostly, as I mentioned, this is SAP applications and the tunnel applications. Okay, and over here, how it looks like. But again, you can see different several pictures in that in Geotech tools. Large open excavation, you see here all these freezing pipes, and then whole thing is frozen, and then you excavate and do the open excavation. So for designing this and for quality control, again, you can use the Geotech tool. We did that and uploaded last year, so you can find out all the materials, quality control, how to design, what are the different software you can use for that. Mostly people use Plaxis and other softwares. And then also this is like what is happening, the SAP freeze wall formation. So what is going to happen? What is unfrozen soil, the frozen soil, how the plasticity or elasticity is going to change. So you can find out from there. So I'm not going to talk about that more theoretical stuff. But again, as I mentioned, so you can find out all the informations in the Geotech tools. Okay, so as I mentioned, this is the process making water bearing strata temporarily impermeable. Freezing is normally used to provide structural underpinning, temporary support, and then also no extra material is needed. So because we are not doing anything. So basically, you're not adding chemicals, we just freeze that water. That's all. So nothing is required. No extra material. And then normally used to provide structure. So this is different application, as I mentioned. I just mentioned to mention that it can be used for any soil, rock formation, regardless of structures, grain size or permeability. Best suited for soft ground rather than rocks. Obviously, the water should be there, right? So you need to freeze the water. Freezing water may be used for any size, safe and depth excavation. The same cooling plant can be used for the job to job. So you can use that, move that like you can use for boring machine or rig to transport the same thing, same freezing system you can use for different site. Okay? I think principal freezing, I'm not going to go in detail over here. So basically, this is another freezing technique. As I mentioned, the Joe Sopko is the one. He's the director for that, the ground freezing company, and we developed that ASC Geotech tools. There are a lot of informations are there, and so this is you see the different pipelines over here. So basically, the header and riser, like the same thing we mentioned with the dewatering technique. So only thing is here in the pipeline, we need to supply either liquid nitrogen or calcium chloride. That's all. Okay. So I think that's all, for this ground freezing. I just went over quickly for the sake of time. So basically, the ground freezing tool, as I mentioned, so in AC, go to the AC site, Geo Institute, Geotech tool. This is the one last year we developed this, all these techniques and everything. Specifically, Joe Sopko is the one is expert in this ground freezing. And a lot of project basically in California and New York where they use this ground freezing technique, especially for the tunnel and the drill shaft foundation. Okay. So this ground freezing and ground heating is when the soil is generally the very soft soil, just heat it, and then just remove the water. But also the properties is also going to change in that situation. So we have not I think in the first slides in ground improvement we mentioned that, but not in detail. Okay. All right. This one is again you need to read that the Geotech tools. There you can find a lot of information. My only thing is here that the different mechanism, how to design that instead of three-phase system like a soil, air, water, and air. So here the ice is coming into pictures. Water, some portion will be ice, some like unsaturated soil mechanics, right? Some portion of the voids are filled with air, some portion is water. Here, some portion of the field is air, and some portion is already nice. Okay. As I mentioned, if you need anything from this geopolymer or durability, we are working on that still. This is a lot of, I know there's in IITs or NITs, a lot of people are doing research on that area. The practical thing is, I know that geopolymer, you need high temperature, but in Australia, people already use that geopolymer. There is a method to use, and then in US, not many people are using here in practically, but I think I'm sure people will be using this geopolymer. It's much more sustainable. The strength is much more compared to the convention. All right. Any questions or anything? I can, if anyone needs that, the paper I mentioned, the 4 paper where from I presented the durability and geopolymer, I can send that paper to everyone if even needed. Which one? I can see that only earlier chart. So where is the chart? Yeah, I click that. So chart preview. The earlier one I can see. I can see the last chat here. Yes, sir. Thank you. That's all. The GGPS one. What about the other chart? Oh, okay. Oh, that's the last one. Last time I mentioned that GGBS is, again, we have seen that the durability, correct? Sometimes, we need to be careful while with the freezing thawing or maybe the wetting drying, right? So the current study, we have seen that if you're using GGBS, so we need to have some activator, either a little bit of cement or lime, or if you are using GGBS with that geopolymer, obviously that's the sodium hydroxide, sodium silicate, it's much better, as you have seen the freezing, but freezing thawing is the worst. You have seen that the earlier studies, and then wetting drying is much better. It can survive. So you need to do different accelerated tests, like freezing thawing and wetting drying. How many cycle it can survive? So then it is much more durable, right? So that is the durability index. So mostly you do the UCS test, you do the freezing thawing cycle, and then whatever the sample survive, if it is in good shape, and then do the UCS test again. So then you can find out the durability index. From there, you can find out how much is the durability index. So you can find out from there how durable. And also, a lot of people are doing like a durability for the concrete. I know that the acid test, and other tests. You can do this for the soil also, soil stabilized, but we have not done that. So I'm sure people can do that.
Please have a look regarding lime stabilization for expensive clay which have higher plasticity index.
Okay, that's why we mentioned already, correct? So initially that at the same time, with the curing period, it is going to they increase the strength, right? So an expensive clay or maybe is more, again, what type of expensive clay, correct? If you're using kaolinite, it's different. If you're using monolinite, it'll be different, right? Again, what type of reaction takes place, we need to check that reaction. And also, even we need to see that the diffuse double layer stuff, how, and the zeta potential, all these things you need to check to study really what is happening in the microstructure level. All right.
That's fine, sir. I think if everything is okay, we can close the session, sir, because the tutorial we have from, I think it's not, what is time now? 10. Yeah, 10. Actually, we have a tutorial, but we will try to circulate the questions so they will solve it themselves if they have any doubts.
Okay.
Yes, sir.
So I think the schedule just I have the only one tutorial session, correct? I think only one tutorial session I have. This one. Yeah. That's one I did it today, but I'm not happy at all. I mean, the way it was going. So, but anyway, what to do?
So you have a 2 hours lecture, sir, from 6:30 to 9:15. 2
Okay.
hours minutes.
So basically the grouting and soil nailing and anchoring, and then the soft soil stabilization and MSC. There are so many topics, but time is short. So that's why I'm just showing click, just showing the slide. That's all, nothing. I mean, just clean out. I don't know what to do. I mean, either you need to just one topic, go in detail, and then otherwise, if you want to cover everything, just go quickly. You cannot just.
So, sir, tomorrow we have a 2 hours.
So if you need all these like in the slides, whatever, although it is recorded, but I don't know if you need all the slides. Original, I put it in OneDrive, so anyone can access that if someone need it. Just only the slides. So that site can be used for teaching or anything. I mean, this is my slides I prepared, but can be used for anyone if you want to use it. Also, I collected from the several sources. And also from my research. I mean, it's an ongoing process, right? So, all right. If someone get benefit or someone is because I compile everything together, so it'll be easy. All right. So anyway, so I just as I'm doing it, like I just go quickly, just touching all this cover all the material, and then so tomorrow we'll be doing this mechanically stabilized retaining wall, and the last one, and the following day is 19th is just only the sustainability aspect, right? Geotechnical engineering. I'll talk more. So that is the one I talked a little bit of the sustainability index, leave it today. I will talk more about that, the greenhouse gas and other things. And how to use it for different industrial materials, waste material. So basically, that's much more sustainable. All right.
Very much, sir.
Thank you so much.
Yeah. No.
Okay. Bye.